Settle in. Get comfortable. Let your breathing slow. Tonight, we're going to take a long, quiet journey through one of the most extraordinary questions you could ever ask about the universe we live in. What would happen if the Milky Way, our galaxy, our home among the stars, simply went dark? Not dimmed, not faded, dark, completely, silently, utterly dark. It is the kind of question that, on the surface, sounds almost too strange to take seriously. And yet, when you sit with it, really sit with it the way you might sit beside a fire and watch the embers drift upward on a winter night, you begin to realize how much it reveals. About light, about time, about how deeply, almost without knowing it, we have always depended on the sky above us. So let's begin slowly, the way this story deserves to begin. With a single, still moment, you are standing outside, somewhere quiet and far from any city. Maybe it's a desert, maybe it's a meadow, maybe it's a mountain ridge you've climbed to 1,000 times in your imagination. The air is cool, the ground beneath you is solid and real, and above you, stretching from one horizon to the other, is the Milky Way. You've probably seen it, or at least seen pictures of it. That long, luminous river of light, that soft, pale band arcing overhead like the ghost of something enormous. On the clearest nights, from the darkest places on Earth, it looks almost solid, a brushstroke of ivory and silver laid across the black of space, so dense with stars that the individual points of light blur together into a single breathing glow. That glow is not decorative. It is not incidental. It is the light of hundreds of billions of stars, most of them so far away that the light now reaching your eyes left its source before human civilization existed. Before writing, before farming, some of it before the first stone tools were ever shaped by human hands. All of it traveling across incomprehensible distances to arrive, quietly, in your eyes on this particular night. And now imagine it gone. In the scenario we are exploring tonight, every star in the Milky Way stops emitting visible light at the same instant. Not a gradual fading, not a slow dimming at the edges while the core holds on. All at once, simultaneously, across the full span of the galaxy, the lights go out. That luminous river overhead, the one that has been there every clear night since the Earth first cooled enough to have a sky, simply vanishes. The band of light disappears, and in its place is nothing but a long, strange darkness where the glow used to be. The sky doesn't look emptier exactly. There are still stars visible, or at least there appear to be. But the river, the sweep of it, the sense of depth and abundance that comes from gazing into the heart of our own galaxy, is simply gone. What's left feels thinner, somehow, quieter, like a room with most of the furniture removed. This is the first and most immediate consequence of a dark Milky Way. Not an explosion, not a catastrophe, at least not yet. Just an absence, a gap in the sky where something luminous and ancient used to live. And already, even in this first quiet moment, you begin to sense how strange and far-reaching the consequences would become. Because among all the stars that have just gone dark is one in particular. One that is not a distant point of light, not a faint ember at the edge of visibility, but the blazing, roaring heart of everything that makes life on Earth possible. When we say every star in the Milky Way has gone dark, we mean every star, including the one that, at this very moment, is on the other side of the planet from you, keeping the rest of the world warm and bright, including the sun. It is easy, perhaps, to hear the phrase, "the sun goes dark," and imagine something gradual, a solar eclipse, a dimming at the edges, some process you could watch unfold. But this would be nothing like that. The light simply stops. In the same instant that the rest of the galaxy goes dark, our star goes dark too. And the consequences of that single fact are so enormous, so immediate, and so total, that they require their own moment of quiet consideration. Without the sun, Earth does not simply become a cold, dark version of itself. It begins immediately to die in the geological, planetary sense of the word. The warmth that keeps the oceans liquid, that drives the weather, that powers every living thing through the slow miracle of photosynthesis, all of it stops at once. The planet begins to cool, not over centuries or millennia, but noticeably, measurably within days. Within weeks, the surface temperature would drop to levels that most life cannot survive. Within months, the oceans would begin to freeze at the surface. Within years, the cold would reach depths that have been liquid for billions of years. This is not something to dwell on tonight. We are here for wonder, not for dread. But it is worth holding briefly, the sheer scale of what the sun means to us. We tend to think of sunlight as something we enjoy, something we miss on cloudy days, something that gives us vitamin D and warm afternoons and golden hour photographs. But sunlight is not a comfort. It is the engine of everything. Every calorie of food you have ever eaten traces back to it. Every breath of oxygen in your lungs was made possible by it. The entire living world, in every corner and crevice of this planet, exists because one medium-sized star happens to be precisely the right distance away, burning in precisely the right way, at precisely the right time in the universe's long history. In a dark Milky Way, all of that ends. But even as that sinks in, there is something else happening, something stranger and in its own way more beautiful even in the darkness. While our sun has gone dark, and while the stars of the Milky Way are no longer shining, the universe beyond our galaxy has not changed at all. The light from other galaxies, distant, enormous, ancient, is still traveling. And without the blaze of our own galaxy drowning them out, some of those galaxies would become, for the first time, genuinely prominent features of the night sky. Andromeda, our nearest large galactic neighbor, sitting about 2.5 million light-years away. On a dark night, even now, with a good eye and a very dark sky, you can just barely make out Andromeda as a faint smudge near the constellation Perseus. Most people have never seen it. It is easy to miss. But in a sky from which the entire Milky Way has been erased, Andromeda would be remarkable. A soft, elongated cloud of light, containing 1 trillion stars, visible to the naked eye in a way it has never truly been before. Our own invisible galaxy lying beneath it, silent and dark, while the light of our nearest cosmic neighbor glows overhead. There is something haunting about that image. Looking up at another galaxy's light while our own has gone silent. Being able to see the home of 1 trillion other suns precisely because our own stars no longer drown them out. The irony is almost poetic. The absence of our galaxy's light making visible what the presence of it had always hidden. But here is where the story becomes genuinely strange and genuinely wonderful in equal measure, and it is worth taking a moment to let it settle properly, because it touches on something fundamental about the nature of light itself. The darkness we have been imagining, the darkness that would fall on Earth the moment our sun went out, the strange emptiness where the Milky Way's glow used to be, that darkness would not, in fact, be universal. It would not arrive everywhere at once. Because light takes time to travel, and time, in the universe, is measured in distances so vast they challenge every ordinary human intuition. When you look at the Milky Way on a clear night, you are not seeing it as it is now. You are seeing it as it was hundreds, thousands, even tens of thousands of years ago, depending on which part of the galaxy you are looking at. The light from stars near the galactic center, about 26,000 light-years away, left those stars 26,000 years ago. At that time, there were no cities on Earth, no agriculture, no writing. The last ice age had not yet ended. And the light from those stars has been traveling ever since, crossing the silent dark of interstellar space, and only now arriving at your eyes. Which means that if the Milky Way went dark tonight, the stars near the galactic center would appear to keep shining for another 26,000 years. The last photons from those stars, already in flight, still have a journey of millennia ahead of them. The sky would lie to us, in a sense, for an extraordinarily long time. Stars that no longer exist, light from suns that have already gone cold, still appearing overhead as bright and steady as ever. The darkness would arrive in layers, spreading slowly inward as the final light from progressively closer stars reached Earth and ended. Some stars near the edge of the galaxy whose light has almost reached us would wink out in decades. Others, farther away, would take centuries, and the most distant parts of our galaxy would keep sending their ancient photons our way for tens of thousands of years after the last of their light was produced. This is not a comforting thought exactly, but it is a strangely beautiful one. The universe keeps its records in light, and light cannot be recalled. Once sent, it continues forever, carrying its message across the dark, indifferent to whether the source that created it still exists. Now consider what all of this would mean for the other great losses that would follow in a dark galaxy. The galactic center, that brilliant, impossibly crowded hub at the heart of the Milky Way, packed with billions of stars far more densely than the quiet suburban arm of the galaxy where our own sun lives, is a place of extraordinary brightness in the night sky, even now. From the southern hemisphere, on a truly dark night, it is a breathtaking sight. A blazing cloud of densely packed light, ancient and enormous, the true heart of our galaxy. In a dark Milky Way, that light would eventually fade, and what remained would be an invisible void, a gravitational center with no light to mark it. A black hole surrounded by the dark remains of stars, all of it unseen, pulling on the rest of the galaxy in silence. And without any of that light, the sky above us would lose something we have almost forgotten to appreciate precisely because we have always had it. On a clear night, far from city lights, the sky glows, not brightly, not like a city, not like anything you could read by, but softly everywhere. A faint luminescence that comes from the combined light of all the stars that are too faint to see individually but too numerous to ignore entirely. This galactic glow, this ambient light of the cosmos, is what makes truly dark skies feel alive rather than merely empty. Stand in a desert or on a remote mountain and look up, and what you see is not blackness. It is deep, a luminous, layered depth that pulls the eye upward and inward at the same time, hinting at distances and scales that no number can really capture. In a dark Milky Way, that glow would be gone. The sky would be darker than any human being has ever seen. Not the familiar dark of a moonless night, but something genuinely more absolute. A darkness with less behind it, less breathing inside it. The kind of darkness that would feel, perhaps, like absence. And without starlight passing through our atmosphere, there would be no twinkling. That gentle shimmer that makes stars feel almost alive, almost present, is caused by the way their light bends as it passes through layers of moving air. Take the stars away, and the sky above becomes still and uniform and flat. Not even the small, animate quality of twinkling would remain to soften the void. For thousands of years, human beings have looked up at the night sky and found something there. A map, a story, a set of familiar shapes and patterns that could be read and followed and passed down from one generation to the next. The constellations, Orion with his belt and sword, the Great Bear lumbering across the northern sky, the Southern Cross guiding navigators in waters far from home, are not scientific categories. They are relationships, lines drawn between stars by human imagination, connecting points of light into figures and animals and heroes and gods. They are the oldest art form we have, older than painting, older than sculpture, as old, perhaps, as language itself. In a dark Milky Way, every one of those constellations would eventually go dark. Orion would lose his belt one star at a time. The Big Dipper would empty and fade. The Southern Cross would drop into darkness. All the patterns that ancient sailors used to find their way home across open water. All the figures that ancient farmers used to track the seasons. All the stories that have been told and retold under clear skies for 50,000 years. Gone. Not immediately because of the time it takes for light to travel, but star by star over years and centuries, the sky would be stripped of every familiar feature until the last remaining light from the farthest star in the last recognized constellation finally arrived and winked out, and the sky was bare. There is something in that image that touches something deep. The night sky, for all of human history, has been the one thing every human being has shared. Every culture, every century, every person who has ever lived has looked up at the same stars, drawn different pictures from them, told different stories about them, but looked at the same light. The Milky Way overhead on a summer night was visible to your most distant ancestors. It would be visible in a world without this scenario, to your most distant descendants. It is, or was, a thread of continuity running through the entire story of our species. To lose it would be to lose something that cannot easily be named. Not just a navigational aid. Not just a decorative feature of the night sky. Something more like a shared inheritance. A common ground between every human being who has ever tilted their head back and wondered what it all was, and where it all came from, and whether anything out there was looking back. And with the sun gone, there would be one final, profound change to the rhythm of life on Earth, or what remained of it. The difference between day and night, that ancient, reliable alternation that has organized living things since the first microbes drifted in the primordial ocean, would cease. Not because the planet would stop rotating, but because with no sun to mark the difference, rotation would become meaningless. The side of Earth facing where the sun used to be would be just as dark as the side facing away. Everywhere, equally and permanently, night. The same cold darkness from pole to equator, from ocean to mountain, from one end of the day to the other, a distinction that would no longer exist. All of recorded history, all of human civilization, all of the daily rhythms that every living thing on this planet has organized itself around for billions of years. Morning and evening, sunrise and sunset, the slow brightening of the east that has meant safety and warmth to every creature that has ever lived. All of it erased along with the light. Let that sit for a moment. Breathe. It's a strange thing to contemplate, the end of the sky's familiar light. Not because it is likely, it is not. Not because it should frighten you, it shouldn't. But because in imagining what we would lose, we begin to see more clearly what we have. The light that falls on your face on an ordinary morning. The stars that appear on an ordinary clear night. The slow river of the Milky Way, visible from a hillside far enough from any city. These things are not ordinary. They are ancient and enormous and extraordinarily unlikely, the product of billions of years of cosmic history unfolding in just the right way. And they are here, still shining. The galaxy has not gone dark. The sun still burns. The constellations are still overhead, waiting for the next clear night, the next pair of eyes willing to look up and trace their old familiar lines. And that is, perhaps, the most restful thought of all. In the last part of our journey, we stood outside under a sky that had just lost its river of light. We watched, in imagination, as the Milky Way's soft glow disappeared from the sky, as the galactic center went dark, as the constellations began their long, slow process of going out one star at a time. We felt, perhaps for the first time, how much of our sense of the sky's aliveness comes from light, ancient, traveling, improbable light, arriving at our eyes from sources that are older than everything we have ever known. But most of that was about distance, about what we would see or stop seeing when we looked up, about the galaxy as it appears from the outside, from the ground, from the particular vantage point of a small planet circling an ordinary star on one of the Milky Way's quieter arms. Tonight, we turn our attention closer to home. Because if the Milky Way went dark, if every star, including our own sun, stopped shining, the consequences would not stay up in the sky. They would come down. Slowly at first, then faster, then absolutely and completely. They would descend from the sky and settle onto the surface of this planet, into its oceans and its atmosphere and its soil, into every living thing that has ever drawn breath on it. The darkness would not remain an abstract, astronomical event. It would become something deeply, immediately, physically real. Let's begin with the thing that might surprise you most, at least at first. When the sun goes dark in our imagined scenario, Earth does not go dark in the way you might instinctively picture. The planet does not stop. It does not spin out of control. It does not tumble away into empty space, suddenly freed from the gravitational pull that has kept it on its steady, reliable path around the sun for 4.5 billion years. Here is why gravity and light are not the same thing. The sun's gravitational field, the enormous, invisible architecture of curved space that holds the entire solar system in its arrangement, that keeps Earth on its near-circular orbit, that prevents the planets from drifting apart into the cold of interstellar space, does not require the sun to be shining in order to function. Gravity is not carried by light. It is a property of mass, and mass does not vanish simply because light does. A dark sun is still a massive sunday. It still sits at the center of the solar system with the same weight it has always had. And Earth, moving through space at the same speed it has always moved, continues to arc around it in the same path it has always traced. The invisible sun still reaches out with its gravitational hand and keeps the planet in its orbit, just as it always has. The year still passes. The seasons still come and go in the astronomical sense. Earth still reaches the same points in its orbit at the same intervals. There is something almost eerie about that. The planet is still circling its star. The star is still holding the planet. The relationship is still intact, still functioning, still mathematically precise. And yet the star is dark and the planet is dying, and the sky above is as empty as it has ever been. Because without light, the sun cannot do the other thing it has always done. The other thing that is, in terms of life and atmosphere and the surface world of this planet, far more immediately important than gravity, cannot warm us. Take a moment to consider what that actually means. Not the abstract version, not the textbook phrase, the sun provides heat and energy. Consider it from the ground up. Consider what the sun's warmth does to this planet in the course of a single ordinary day. The moment sunlight touches the surface of the Earth, it begins a cascade of processes. It warms the land unevenly because different surfaces absorb and reflect heat differently, and this uneven warming is what creates wind. It strikes the surface of the ocean and evaporates water into vapor, which rises into the atmosphere and eventually falls again as rain, keeping the water cycle in motion. It reaches the leaves of every plant on the surface and is captured, quietly and efficiently, by the molecular machinery of chlorophyll, converted from light into chemical energy that becomes the foundation of nearly every food chain on Earth. It reaches your skin and is absorbed, triggering reactions that produce vitamin D and set your body's internal clock for the day ahead. All of that happens every single day, every moment the sun is above the horizon, and has been happening without interruption for longer than life itself has existed on this planet. Take the sunlight away, and within hours you can begin to feel the absence. Take it away permanently, and within days the effects become impossible to ignore. 1 week. That is approximately how long it would take, on average, for the surface temperature of the Earth to drop below freezing everywhere in the world. Not at the poles where it is already cold everywhere. The tropics, the equatorial rainforests, the warm coastal plains, the sun-baked deserts that have never known frost. Within 1 week without sunlight, all of it would cross below the freezing point of water, and the slow, irreversible process of planetary glaciation would begin. 1 week is not very long. 7 days. The length of time between 2 Sundays. the time it takes to read a few books or finish a short project or plan a trip. And in that span, the entire thermal balance of a planet that has maintained livable temperatures for hundreds of millions of years would shatter. The reason the collapse would be so swift is that Earth's warmth is not stored particularly deeply. The planet has an enormous hot interior, yes, a molten core that generates some heat of its own, but the surface, where life exists, is a thin shell warmed almost entirely from above. The atmosphere holds some heat in the way a blanket holds body warmth, but without a continuous supply of solar energy, that stored warmth would drain away quickly. The atmosphere is not nearly a good enough insulator to keep the surface warm on its own for long. Within a month, temperatures in many parts of the world could fall to the range of -40 degrees or colder. Within a year, the oceans would begin to freeze at the surface in all but perhaps the deepest, warmest regions. Within decades, the ice would thicken and advance. Within centuries, an Earth without sunlight would become something almost unrecognizable. A frozen, silent world wrapped in ice and darkness, its oceans locked beneath glaciers miles thick, its atmosphere gradually thinning as gases condensed and fell as frost. But before we get to centuries, the effects on the living world would begin almost immediately. And they would begin quietly and invisibly with the plants. Plants are, in a sense, the planet's most fundamental life support system. Not because they are the most complex or the most interesting creatures on Earth, but because they are the ones that do the most basic and irreplaceable work. They take light and convert it into energy that everything else can use. Every food chain, every ecosystem, every animal, including every human being, ultimately depends on that process. We eat the plants, or we eat the things that eat the plants, or we eat the things that eat the things that eat the plants, but trace it back far enough and the chain almost always ends at a leaf in the sunlight. Without sunlight, that chain breaks at its very first link. Plants would begin to die within days of the light disappearing. Not all at once. Seeds can survive for a long time in cold and darkness, and some roots and tubers might persist for weeks or months. But the green, photosynthesizing parts of the plant world, all the leaves and stems and blades of grass that are alive precisely because they are converting sunlight into sugar at this very moment, those would begin to fail almost immediately. Without energy input, the cellular processes that maintain them cannot sustain themselves. They would wither, brown, and freeze, joining the deepening layer of ice and frost on the surface. As the plants died, the animals that depended on them would follow. Herbivores first, then the carnivores that relied on them. The food webs that have taken hundreds of millions of years to evolve into their current intricate complexity would collapse level by level, losing species faster than any extinction event in the planet's history. And as the plants died, there would be another consequence that is easy to overlook but extraordinarily important. Oxygen production would stop. The oxygen in Earth's atmosphere did not come from nowhere. It was made molecule by photosynthetic life over billions of years. And while the atmosphere holds enough oxygen to sustain animal life for quite a long time even without new production, the principle is clear. The machinery that made the air breathable runs on sunlight, and without sunlight, it stops. The planet's weather would begin to change almost as quickly as its temperature. This might seem counterintuitive at first. Weather feels like its own system, self-sustaining, driven by complex interactions between air masses and pressure systems and moisture. And in a sense, it is. But all of that complexity is ultimately powered by something very simple: the uneven heating of the Earth's surface by the sun. Wind exists because some parts of the surface are warmer than others, which makes air rise in some places and fall in others, creating flows that we feel as breezes or storms. Ocean currents exist for the same reason, redistributing heat from the tropics toward the poles. Evaporation exists because sunlight warms the ocean surface enough to lift water vapor into the atmosphere. Rain exists because that vapor rises, cools, and condenses. Take away the sun, and all of these systems begin to slow. Not instantly. There is momentum in the atmosphere and the ocean, years and decades of stored energy still working its way through the system. But the engine that drives it all is gone. And without that engine, the weather would gradually grind down toward stillness. Toward a cold, calm, airless quiet. Look up on one of those first dark nights, and you would notice something unexpected. The moon is gone. Not gone exactly. The moon is still there, still in orbit, still moving through its phases. But you would not be able to see it. The moon, which on a clear night can be bright enough to cast shadows and illuminate a landscape well enough to walk by, shines not with its own light but with the sun's. It is a mirror, a pale and cratered mirror, reflecting sunlight back toward Earth. Take the sunlight away, and the moon goes dark along with everything else. It becomes invisible, a dark disk passing silently through a dark sky, perceptible only as a region where the stars behind it are briefly blocked. Its presence would be felt only as an absence, a moving shadow within shadows. And without the moon's reflected light, the darkness of night would reach a depth that very few people living today have ever experienced. Even on the darkest nights in the most remote locations on Earth right now, there is some light from the moon if it is up, from the stars, from the diffuse glow of the Milky Way, from the faint luminescence of the upper atmosphere. There is always something. The human eye, given enough time to adjust, can almost always find some photon to work with, some trace of light to navigate by. In a world without the sun, and with the Milky Way's own stars slowly going dark, the surface of the Earth at night would be dark in a way that goes beyond what most people have the vocabulary to describe. Not the comfortable dark of a bedroom with the curtains drawn. Not the temporary dark of a power outage. Something more total and more disorienting. A darkness in which the normal intuition that shapes and distances are available somewhere, if you could only see a little better, would simply not apply. There would be nothing to see better. There would be nothing there. Shadows, which we think of as a feature of darkness, require contrast to exist. A shadow is defined by the difference between a lit area and an unlit one. In a world with no light source, there are no shadows. There is only dark, uniform, and featureless across every surface. The landscape would not be shadowed, it would be invisible. The texture of the world, all the hills and valleys and surfaces and edges that we navigate so effortlessly in daylight, would be present only to touch, not to sight. And there is a smaller thing, a gentler loss that is worth mentioning quietly here, because it speaks to what the sun means to the experience of being alive on this particular planet. Sunsets would end. That daily spectacle of color, the reds and oranges and purples that spread across the western sky in the minutes before full darkness, the way the light changes quality as it travels through more atmosphere at low angles, the way the clouds catch fire with reflected gold, that experience, which has been witnessed by every human being who has ever lived and which has found its way into more paintings and poems and moments of quiet gratitude than almost any other natural phenomenon, would simply stop happening. Not because the planet had stopped rotating, but because there would be nothing in the sky to color the horizon. No blazing point of light sinking below the edge of the world. Just a uniform darkening, barely distinguishable from the dark that came before, signifying nothing in particular. Rainbows, too, would be gone. Those transient arcs of divided light that appear when sunlight passes through water droplets in the air and is bent into its component colors depend entirely on a specific geometry. A bright point source of light, water droplets in the air, and an observer at just the right angle. Remove the sun, and the geometry collapses. There is no light to bend, no spectrum to reveal. The rain could still fall for a time while the atmospheric water cycle still had some momentum, but it would fall in darkness, producing nothing but wet and cold, no color, no arc, no brief reassurance that the world is full of hidden beauty. There is something called the zodiacal light that most people have never heard of, and yet it is one of the stranger and more beautiful features of the night sky for those who have sought it out. On very dark, very clear nights, in the weeks after sunset or before sunrise, there appears a faint, diffuse glow stretching up from the horizon along the path of the zodiac. A soft pyramid of light, pale and ghostly, that can look almost like the beginning of dawn even in the middle of the night. This glow is sunlight, not reflected by the moon or any solid body, but scattered by the vast cloud of tiny dust particles that fills the plane of the solar system, left behind by comets and asteroid collisions over billions of years, drifting in slow orbits around the sun and scattering its light outward in all directions. Without the sun shining, the zodiacal light would vanish with everything else. The dust would still be there, those ancient, wandering particles, remnants of the solar system's formation, would continue their slow orbits undisturbed. But they would have nothing to scatter. They would become invisible, just another component of the invisible, lightless solar system, present but silent. And eclipses, those extraordinary, humbling events when the moon passes between the earth and sun and the sky goes briefly dark in the middle of the day, revealing the sun's corona and silencing the birds and dropping the temperature in seconds. Eclipses would still technically occur. The orbital mechanics that produce them, the precise alignment of sun and moon and earth, would continue. But they would become nearly impossible to notice. An eclipse is dramatic precisely because it interrupts brightness, because it creates a sudden, disorienting absence in something that is normally there and overwhelming. In a sky where there is already no sun, the moon passing in front of the place where the sun used to be would be a non-event. An astronomical footnote, a ghost of a phenomenon, going through the motions of something that used to matter, in a sky too dark and too still to notice. Take a breath. Let the darkness of this imagined world rest quietly in your mind for a moment. It is a dark place, this earth without its star. Colder each day, quieter each week. Its skies are empty of sunsets and rainbows and zodiacal glows and the comfortable pale disk of the moon. Its surface moving toward ice and stillness. Its food chains fraying from the base upward. Its weather systems slowing toward a cold, calm, featureless pause. And yet here you are, warm. The sun has not gone anywhere. It will rise again tomorrow. It has been rising every single day for 4.5 billion years. And when it does, it will do all the things we have been imagining it no longer doing. It will warm the land unevenly and make the wind blow. It will lift water from the ocean and send it inland as rain. It will strike the leaves of every plant and fill them with energy. It will color the horizon at the end of the day with every shade of orange and gold and rose that it has been painting across the sky since long before there were eyes to see it. The sun is still there. The planet is still warm. And somewhere on a clear night, from the right place and the right darkness, the Milky Way is still overhead. Rest now. The sky will take care of itself. There is a particular quality to deep cold that is different from ordinary cold. The cold of a winter morning, the cold of a refrigerator, even the cold of a mountaintop in a storm. These are uncomfortable, perhaps dangerous if you are unprepared, but they are temporary. They exist within a range that the living world knows and has adapted to. Flowers bloom after frost. Animals grow winter coats. Ice melts in spring. The cold comes and goes, and life accommodates it, bends around it, waits it out. The cold we are imagining tonight is not that kind of cold. It is the cold of space itself. The cold that exists in the vast, empty regions between stars, where no sun has ever warmed anything, where the temperature hovers just a few degrees above the lowest temperature that physics permits anything to reach. Absolute zero. The point at which molecular motion essentially stops. The point at which matter becomes as still and silent as matter is capable of becoming. The space around Earth sits near that temperature right now, at this very moment, just a few degrees above absolute zero, out beyond the thin shell of warmth that sunlight creates around our planet. That warmth, that comfortable habitable zone, is not a feature of the universe. It is an exception to the rule. It exists only because a star happens to be close enough to push back against the cold, to pour enough energy into this small region of space to keep a thin layer of rock and water and air warm enough for liquid water, warm enough for chemistry, warm enough for life. Remove that star and the exception ends. The cold that has always been waiting just above the atmosphere would begin to press downward, slowly and completely, and without any possibility of reversal. Earth, in a galaxy that has gone dark, would begin the long, slow process of becoming what space has always wanted it to be. Cold, still, silent, a frozen rock in the dark. This transformation would not happen all at once, and that is worth understanding because there is something in the gradual nature of it, in the way the planet would hold on, in the places that would resist longest, in the life that would persist in the deepest and darkest corners long after the surface had surrendered. That is, in its own way, remarkable. Consider first the scale of what space's cold actually means. When we say the temperature in space near Earth hovers near absolute zero, we are talking about temperatures in the range of -270 degrees Celsius. The coldest naturally occurring temperature ever recorded on Earth's surface was around -90 degrees in Antarctica. The average temperature across Earth's surface today is about 15 degrees above zero. The difference between those two extremes, between a livable planet and the cold of surrounding space, is roughly 280 degrees. That is the gap that sunlight fills. Every single day, sunlight pours enough energy into the Earth system to maintain that gap, to keep the surface warm against the constant, patient pressure of the surrounding universe trying to equalize the temperature. Without sunlight, the planet would begin losing that warmth immediately. The atmosphere would radiate heat into space. The land would radiate heat into the atmosphere and then into space. The oceans would radiate heat from their surfaces. Everything that is warm would begin giving its warmth away, and nothing would be coming in to replace it. The process would be gradual at first and then accelerate. Within a week, as we imagined before, global temperatures would fall below freezing. Within a month, the cold would deepen significantly. Within a year, the surface would be approaching the kinds of temperatures currently found only in the most extreme environments on Earth. Within decades, the transformation of the oceans would be well underway. The oceans, they would be, in many ways, the most dramatic part of the story. They are enormous. They cover more than 70% of the planet's surface and contain a volume of water so vast that it is almost impossible to describe in terms that feel real. They have an enormous thermal mass. They can absorb and store heat far more effectively than the land or the atmosphere, and they would give up their warmth more slowly as a result. But slowly is not the same as never. The surface of the ocean would freeze first. A thin skin of ice, forming on the calmest and coldest regions initially, the polar oceans first, then spreading toward the equator as the years passed. That ice would reflect sunlight back into space, but of course, in our scenario, there is no sunlight to reflect. The ice would simply form and thicken and spread, accumulating year by year, pressing downward from the surface. Beneath that thickening layer of ice, things would be different for a very long time. The deep ocean holds an enormous reserve of heat, accumulated over billions of years of solar warming, mixed and circulated through the global ocean system. In the deepest regions, the water would remain liquid for potentially thousands of years after the surface had frozen over. A vast, dark, cold ocean sealed beneath a ceiling of ice miles thick, its temperature slowly declining toward the point at which even deep seawater freezes. But not all of Earth's heat comes from the sun. Some of it comes from the planet itself. Beneath your feet at this very moment, the interior of the Earth is hot. Not just warm, genuinely hot, the product of two sources that have nothing to do with sunlight. The first is the residual heat from the planet's formation, the warmth left over from the violence of accretion, when billions of rocks and dust particles smashed together and their kinetic energy converted to heat, building the planet up over millions of years. The second is the ongoing decay of radioactive elements in the Earth's interior: uranium, thorium, potassium, slowly releasing heat as their atoms break apart, warming the rock around them, driving the slow convection of the mantle and the movement of the tectonic plates. This geothermal heat is real and significant. It is what drives volcanoes and hot springs and the heat you would feel if you drilled deep enough into the crust. But it is also, compared to what the sun provides, quite modest. The sun delivers about 10,000 times more energy to the Earth's surface than the entire planet's internal heat does. Geothermal energy is enough to keep the deep interior molten and to warm certain specific locations significantly. It is not enough to warm the surface against the cold of space once sunlight is removed. Over geological timescales, millions and tens of millions of years, even the deep interior would slowly cool. The radioactive elements that produce heat decay at known rates, and eventually their contribution diminishes. The residual heat of formation, already much diminished from what it was 4 billion years ago, would continue to escape. The planet would cool from the surface down, layer by layer, retreating from the cold above but losing ground slowly and continuously, until even the deep rock was cold and the core itself had stilled. But on shorter timescales, the ones we can more easily imagine, the geothermal heat would matter. It would matter enormously to whatever life remained. Imagine the surface of this frozen Earth. The forests are gone first, or rather, they are there, but they are dead and frozen. The great temperate forests, the boreal forests, the tropical rainforests, all of that extraordinary complexity of living wood and leaf and soil, the product of millions of years of evolution, frozen in place. Trees standing dead in fields of snow and ice, their branches bare, their roots locked in frozen soil, gradually buried under accumulating snowfall that never melts. In some places, ice would pile up to extraordinary depths. Pressing the dead wood flat, compressing it into the ground. Landscapes that were once full of motion and color and sound. Birds and insects and wind through leaves, silent now and white and motionless. The lakes would freeze completely, not just at the surface as they do in ordinary winters, but all the way down. The shallow lakes first, then the deeper ones, their heat eventually extracted and radiated away, until even the deepest lake beds were locked in ice. The ice over some of these frozen lakes, and over shallow coastal areas of the former ocean, would build up to extraordinary thicknesses. Sheets of ice miles deep, pressing down on everything beneath them with enormous weight. The kind of ice that can deform rock over geological time. Abandoned cities, the infrastructure of human civilization, already empty of their inhabitants who would not have survived in this world, would be slowly buried. Not violently, not dramatically. Slowly, under accumulating snow that had no summer to melt it, under ice that crept gradually over structures and filled streets and worked its way between stones and slowly, patiently dismantled everything that had been built. Ice is patient. It has always outlasted everything that human beings have made. Against this backdrop of cold and stillness and slow burial, the volcanoes would be extraordinary. They would still exist. The tectonic processes that drive volcanism are powered by the internal heat of the Earth, not by sunlight, and those processes would continue at least for a very long time. And in a world that had gone completely dark and cold, a volcano would be something almost impossibly dramatic. A vent of genuine heat and light in a landscape that had none. Lava flows glowing orange and red against the ice, visible from enormous distances in the absolute darkness. Ash clouds rising into a sky that had nothing else in it. Steam where the lava met the ice, the only weather left on the planet. It is not hard to imagine that these places would become, in a world with any remaining life, the most significant points on the entire surface of the Earth. The only places where the ground is warm. The only places where light exists above the surface. If any surface-dwelling life had managed to survive, and the chances would be extraordinarily slim. It would eventually find its way toward the volcanoes, toward that warmth and that glow, and cluster there at the edges of the livable warmth that radiated outward into the cold. But the more likely refuges for life would not be on the surface at all. Deep underground bunkers, the kind that have been built or imagined in various forms throughout human history, designed to be self-sufficient and isolated from the surface, could theoretically function for a time. Sealed environments with their own power sources, their own recycled air and water, their own controlled temperatures. The deeper the better, to take advantage of geothermal heat from below rather than fighting the cold pressing down from above. In the rock at sufficient depth, the temperature remains above freezing indefinitely, powered by that slow, patient radioactive decay in the planet's interior. There, in the dark and the quiet, a remnant of surface life might persist, changed, reduced, deeply strange compared to the world it had come from, but alive. And deeper still, in the ocean, where the ice above had not yet reached the bottom, where geothermal vents on the seafloor were still pumping warm, mineral-rich water into the dark. Life would have been there long before the sun went out, and it would continue. Hydrothermal vents are one of the most remarkable things on Earth, and they deserve a moment of quiet appreciation here. They exist in the deepest parts of the ocean, at places where the tectonic plates pull apart or press together and the crust thins enough for the heat below to come through. They are chimneys of hot water, rich in minerals and dissolved gases, rising from the seafloor into the cold ocean above. And around them, entirely independent of sunlight, entirely independent of the photosynthesis that powers almost everything else on the surface, extraordinary communities of life have built themselves from scratch. Tube worms that can grow to enormous sizes, ghostly pale crabs and shrimp navigating by heat sensors rather than eyes, mats of bacteria covering the rocks, drawing their energy not from light but from the chemical reactions between the vent water and the surrounding ocean, a process called chemosynthesis, the solar-independent cousin of photosynthesis. These organisms do not need the sun. They have never needed the sun. They are powered by the same geothermal heat that will outlast everything on the surface by millions of years. In a dark Milky Way, these communities would continue. The surface world would freeze. The forests would die. The skies would go silent. And at the bottom of the ocean, in the hot, mineral-rich water around hydrothermal vents, life would carry on as it had been carrying on for perhaps billions of years, quietly in the dark, unconcerned with what was happening above. There are other survivors worth considering. The organisms that live in caves, not just sheltering there temporarily, but truly adapted to cave life, dependent on it, shaped by millions of years of evolution in environments with no light. Cave fish that have lost their eyes because eyes were never useful in their world. Cave insects and crustaceans and microbes that have built entire ecosystems around the chemistry of rock and water rather than the chemistry of sunlight. These organisms live in conditions that are, in some ways, already quite close to what the frozen surface would become. Dark, cold, still powered by chemistry rather than light. In a world without the sun, these cave communities would not need to adapt. They are already living in the dark, already surviving on resources that have nothing to do with the surface world. They would become, in a strange inversion of the usual order of things, not the marginal and obscure organisms we tend to think of them as now, but the inheritors. The forms of life best suited to what the world had become. This thought extends beyond Earth, when you allow the imagination to reach a little farther. In a Milky Way that has gone dark, all its stars extinguished, all its planetary surfaces frozen, there would still be other worlds. And not all of them would lose their warmth at the same rate. A planet with a thick, dense atmosphere retains heat differently than Earth does. Venus, for example, has an atmosphere so thick and so rich in carbon dioxide that it creates a greenhouse effect so powerful the surface temperature is hot enough to melt lead. This despite being no closer to the sun than it is. In a galaxy without stars, Venus would cool, yes. Eventually, it too would surrender to the cold of space. But the process would take longer. The thick atmosphere, like a very good blanket, would slow the escape of heat significantly. For a time, perhaps a long time, a Venus-like world might remain warmer than its surroundings, a bubble of residual heat in an increasingly cold universe. These worlds would not stay warm forever. No atmosphere is a perfect insulator, and without any energy input to replace what is radiated away, the heat loss is inevitable. But they would stay warm longer. And on the timescales that matter to life, decades, centuries, perhaps even millennia, that additional time could be the difference between survival and extinction. It is an odd comfort, in a way, the idea that even in a completely darkened galaxy, the universe would not go cold all at once. That here and there, for varying lengths of time, pockets of warmth would persist. That life, which has shown itself on this planet to be extraordinarily adaptable and persistent and inventive in finding ways to survive in unexpected places, might find those pockets and make use of them. The deep-sea vents would keep their warmth. The cave ecosystems would keep their darkness and their chemistry. The geothermal heat deep beneath the frozen surface would keep its slow, patient warmth. And somewhere in the cold dark of a starless galaxy, life in its most basic and resilient forms might still be finding ways to persist, to draw energy from what remains, to continue doing the one thing that life has been doing on this planet for 4 billion years. Going on. That is perhaps the most remarkable thing about life, when you think about it in these extreme terms. Not that it thrives in good conditions. Any complex process can sustain itself when conditions are ideal. What is remarkable is the persistence. The way life has found footholds in conditions that seem, from the outside, completely inhospitable. The way it fills cracks in rock and vents in the ocean floor and the dark interior of glaciers and the chemically poisonous water of volcanic hot springs. Life does not require comfort. It requires only enough. Enough warmth. Enough chemistry. Enough time. Even in the coldest, darkest version of Earth we have been imagining tonight, there would still be enough somewhere. In the deep dark water above a hydrothermal vent. In the still silence of a cave a mile below a frozen surface. In the warm rock deep beneath the ice, where the planet's own heat keeps the temperature just barely on the right side of the line. Not much. Not the abundant, extravagant, joyful complexity of the living world we know now, but something, a thread of continuity, a pulse in the dark. Let that thought carry you gently toward rest. The living world is resilient beyond imagining. The cold of space is real and enormous and patient, but life has been here longer than the cold has been trying to win, and it has not surrendered yet. The planet is still warm. The vents in the deep ocean are still flowing. The caves still have their quiet ecosystems moving in the dark. And above all of it, still burning, still warming this thin shell of air and rock and water just enough. Still holding the cold at bay after 4.5 billion years, the sun. It has not gone anywhere. It will be there tomorrow. We have spent some time now in the cold and the dark, moving through a world that has lost its star and begun its long surrender to the patience of space. We have watched the forests freeze and the oceans seal over and the volcanoes glow against the ice like scattered embers in an enormous hearth. We have found life in the deep places, in the vents and the caves and the warm rock far below the surface. And we have held onto the thought that persistence is one of life's most fundamental qualities. That something, somewhere, would still be alive. But tonight, in this fourth part of our journey, we turn our attention to something more specific, more immediate, more human. Because in imagining a world without the sun, it is one thing to think about the physics of planetary cooling, or the collapse of food chains, or the survival of chemosynthetic microbes in the deep ocean. Those are real and important things, and they illuminate something true about how life and energy and warmth are all connected. But at some point, the imagination turns naturally to something closer, to people, to what human beings would actually do and feel and build and lose in the long darkness of a world without its star. This is that part of the story, and it begins, as so many human stories do, with the sudden failure of something we had come to take entirely for granted. The moment the sun went dark, every solar panel on the surface of the Earth would stop producing electricity. Not gradually, not over days or weeks as the light slowly faded. Immediately, in the same instant the sunlight ceased, every photovoltaic cell on every rooftop, in every solar farm, on every satellite relying on solar power, would go from producing energy to producing nothing. The conversion of sunlight into electricity is a real-time process. There is no stored sunlight in a solar panel, no reservoir of captured photons to draw on for a few more hours. The panel works when the light arrives and stops when the light stops. This would matter enormously because the world has come to depend on solar power in ways that continue to grow. But even before that dependence became as widespread as it is, the larger issue is what the disappearance of sunlight does to all the other energy systems that human civilization runs on. The wind that drives wind turbines is driven by solar heating. The rain that fills hydroelectric reservoirs comes from solar-powered evaporation. Even the fossil fuels that modern civilization burns so extensively are, in the most fundamental sense, stored sunlight, the compressed remains of ancient organisms that once captured solar energy through photosynthesis, preserved in the Earth's crust for hundreds of millions of years. Take the sun away, and the energy economy of the entire planet faces a reckoning that goes far deeper than any policy debate or market disruption. The question would stop being which energy sources are most efficient or economical. It would become something much more urgent. Which energy sources do not depend, even indirectly, on the sun? The answers are few, and they would immediately become the most precious things in the world. Nuclear power, both fission, which splits heavy atoms, and potentially fusion, which joins light ones, draws on energy that has nothing to do with sunlight. Geothermal energy, as we have explored, draws on the interior heat of the planet. These would become the cornerstones of whatever human energy civilization managed to maintain itself in the dark. Everything else would slowly fail. And in the early period of the darkness, before most of those alternative systems had been scaled to meet the need, there would be a strange and poignant contrast visible from above. The surface of the planet, already beginning to cool, would be dark almost everywhere. The natural world, stripped of its solar energy, would be silent and lightless across most of the globe. But where the human cities were, there would be light. Not much by the standards of a normal world. Not the blazing, extravagant light pollution that currently renders the Milky Way invisible from most populated places on Earth. But warm, visible, unmistakable light. The glow of street lamps and windows and power plants and all the accumulated luminosity of human settlements, shining upward into the dark sky like scattered lanterns in an enormous, cold room. From space or from a great distance, they would be remarkable. These small, bright islands in a world of absolute darkness. Not natural features, not volcanoes or bioluminescent oceans or auroras. Human features. Evidence of a species that had not yet given up. That was still, somewhere inside those warm lit spaces, thinking and planning and arguing and grieving and doing all the complicated, irreducible things that people do when they are alive and together and trying to figure out what comes next. The atmosphere, in the early years of the darkness, while it still contained moisture and temperature gradients, would do something strange with the light from those cities. Ice crystals forming in the cold air above human settlements would catch the artificial light and scatter it, creating faint glowing halos and columns of light above the inhabited areas. A kind of light pollution in reverse, a reflection of human presence projected upward into a sky that had no other source of illumination. The skies above a lit city would glow faintly while everything around it was completely dark. An eerie, beautiful effect, a marker, a signal visible from great distances in the frozen landscape, saying, "Here, in this place, some warmth remains." How long those surface cities could be maintained would depend entirely on energy. As long as the reactors ran and the geothermal plants held and the fuel lasted, the lights could stay on and the heating systems could keep working against the relentless cold pressing in from outside. But the cold would always be pressing, and the surface eventually would become untenable. The temperature would drop too far. The infrastructure would begin to fail. Pipes would freeze. Materials would contract and crack. The practical challenge of maintaining surface structures against temperatures that would eventually rival the coldest places in the solar system would become insurmountable. And so, in the imagination of this long darkness, the thought that follows almost naturally is, what if humanity went underground? It is not as strange an idea as it might sound. Human beings have been building underground for thousands of years, for shelter, for storage, for defense, for spiritual purposes. The technology of underground construction is well developed. And the deeper you go, the warmer it becomes. As we have noted, the geothermal gradient that keeps the deep earth warm provides a resource that is genuinely independent of the sun. At depths of a few kilometers, the rock temperature is comfortably above freezing even without any artificial heating. Deeper still, it is genuinely warm. An underground civilization would be a profoundly different kind of human society from anything in our history. Not just architecturally, but culturally and psychologically. The organizing principles of life, the rhythms of day and night, the seasonal changes, the sense of being embedded in a natural world with a sky and a horizon and weather, all of that would have to be either replaced or abandoned. The residents of an underground city would live their entire lives within constructed spaces, under artificial light, with the rock above them rather than the sky. And the geothermal sources that would power these underground settlements would not be evenly distributed. They would be concentrated in specific geological regions, places where the crust is thin, where tectonic activity brings heat closer to the surface, where hot springs and volcanic activity provide more accessible warmth. And this uneven distribution of what had become the most valuable resource on the planet would, with considerable historical predictability, become a source of conflict. Energy in any civilization is power in the most literal sense. It is the ability to stay warm, to manufacture things, to maintain complex systems, to keep people alive. In a sunless world where geothermal energy was the primary resource for human survival, the places that had it would be extraordinarily valuable, and the places that did not would be desperate. The dynamics of that situation are not difficult to imagine. They would look, in many ways, like the dynamics of resource competition throughout human history, except with higher stakes than almost any previous version, because the resource in question would not be prosperity or advantage but survival itself. But human beings have always done something remarkable under extreme pressure. They have adapted, not just technologically, though technological adaptation would be essential and extraordinary, but imaginatively, culturally. They have found ways to create meaning and comfort and beauty even in conditions that seem to offer none of the raw material for any of those things. Consider the ceilings of those underground cities. In a world where the sky has gone dark and cold and there is nothing above the surface worth looking at, the sky still exists in human memory, in human need. The impulse to look up at something vast and star-filled and full of quiet wonder does not disappear simply because the actual sky has ceased to provide it. If anything, the loss would make the impulse stronger, more acute, more deeply felt. It is not difficult to imagine the engineering turning toward that need. Digital displays of extraordinary scale and resolution. Curved ceilings in public spaces designed to project not just static images but dynamic, moving renditions of skies that no longer existed above ground. A sunset playing out across the ceiling of an underground plaza, the colors shifting from gold to amber to deep violet, the quality of the light changing as the simulated sun descended. the space filling with the kind of warm, horizontal light that every human nervous system evolved to associate with safety and the end of a day. People stopped to watch. Children who had never seen a real sunset, who had been born underground and would likely die underground, watching something their ancestors had seen every day of their lives without noticing, and feeling the pull of it without ever having experienced the original. The stars would follow. Digital planetariums built not as scientific instruments but as public spaces. Vast domed rooms where the night sky could be reconstructed in precise detail. The Milky Way arcing overhead as it used to appear from a dark hillside, every constellation in its place, the soft glow of the galactic core visible toward the south. People going there to sit and look up in silence, the way people now go to cathedrals or parks or the edge of the ocean when they need to feel small in a way that is comforting rather than frightening. And beyond the underground displays, there might be something even more ambitious, something oriented outward rather than inward. The idea of creating artificial light structures in orbit, not to warm the planet, because nothing of a scale that human engineering could achieve would meaningfully replace the sun's energy output, but for something else. For the psychological function that stars have always served. To give people something to look up at. Something that glowed in the night sky above the ice and the darkness, visible to anyone who found a way to the surface and looked up. Not a real star. Not anything that could be mistaken for one up close, but a light in the sky, a reminder that something still burned, that the universe had not gone entirely dark. There have always been places in the night sky that human cultures oriented themselves around. A whole star, a particularly bright planet, a rising constellation that marked the planting season. The psychological function of a known light in a fixed or predictable location in the sky is not trivial. Provides orientation. It connects the individual to something larger than themselves. It is, in a modest and ancient way, a form of comfort. In a sky with nothing in it, that function would be missing. And human beings, who have always found ways to replace what they have lost, might try to put something back. The star museums would come from the same impulse. Not just digital displays, but archives. Preserved experiences of the sky as it was. Some of them are scientific in their orientation. Precise records of every cataloged star, every observed galaxy, every mapped constellation, maintained for future generations or future researchers. But others would be something different. Experiential. A room you could enter that would recreate, as accurately as possible, the experience of lying in a field on a summer night and watching the Milky Way appear as your eyes adapted to the darkness. The sound of crickets, the smell of grass, the specific quality of the dark, the way the stars seem to breathe. These things would matter. They would matter in ways that are hard to articulate precisely but easy to recognize, because they touch something about what it means to be human that is not entirely reducible to survival requirements. People do not need beauty to survive in the biological sense. They do not need art or memory or the feeling of lying under stars. But something in human experience has always oriented itself toward these things, has always reached for them even under the most difficult circumstances, has always found in them something necessary that purely physical survival does not provide. The scientific literature on light and human well-being is extensive and consistent. Natural light, sunlight, specifically with its particular spectrum and its daily rhythm of change, is deeply integrated into human physiology. The mechanisms by which light regulates the circadian rhythm, the internal clock that governs sleep and waking, and the timing of hormonal cycles, depend on specific wavelengths that sunlight provides. Exposure to natural light is associated with mood regulation, with alertness, with the proper functioning of biological systems that evolved in environments where sunlight was a daily constant. Deprive human beings of that light for long enough, and the effects are real and significant. Disrupted sleep, depressed mood, reduced cognitive function. The increased prevalence of these effects in regions that experience very long winters is well documented. It has a clinical name, and millions of people around the world experience it every year in its milder forms. Now extrapolate that seasonal deprivation to something permanent, to generations raised entirely in artificial light, in underground spaces with no exposure to sunlight because sunlight no longer exists. The physiological adaptations that would eventually occur over many generations, if the species survived long enough, are genuinely unknown. The psychological effects in the shorter term would be a serious and immediate concern. And beyond the physiological, there is something else. Something harder to measure, but perhaps even more significant. The meaning of the sky. Human beings have always looked up and found something there. Not just light and navigation and beauty, but a sense of place, a sense of scale, the feeling of being embedded in something vast and ancient and continuing, something that existed long before you and will exist long after, something that does not particularly need you but accepts your gaze without complaint. The night sky in all of human history has been the most universally available experience of that feeling. You did not need to be educated or wealthy or fortunate to walk outside on a clear night and look up and feel, for a moment, the particular vertigo of knowing that those lights were not ceiling decorations but actual places, actual suns, actual distances that the mind cannot truly encompass. That feeling, small but not alone, brief but connected to something vast, is one of the stranger gifts of being alive on this particular planet in this particular universe. And in a world where the sky was genuinely, permanently, completely empty, its absence would be felt in ways that went well beyond inconvenience or aesthetic loss. It would remove something from the human experience of being alive that had been present since the first human beings looked up with curious eyes and tried to make sense of what they saw. The isolation would be profound. Not physical isolation. An underground city might have many people in it, connected to other underground cities by whatever communication networks remained functional. But a particular kind of cosmic isolation. The feeling of being enclosed, of the universe having contracted from something vast and luminous and full of mystery to something small and dark and sealed. The ceiling of rock above instead of the infinite depth of the sky. The artificial light of constructed spaces instead of the ancient, traveling light of distant suns. Human beings are adaptable beyond almost any other measure. Given enough time, given enough necessity, we adjust. We build. We create meaning in the spaces where meaning has been removed. The underground cities would have their own cultures, their own art, their own ways of making sense of the world they had inherited. The children born into them would not feel the loss the way their grandparents had. The sky they had never seen could not haunt them the way it haunted those who remembered it. The digital sunsets and star museums would be their inheritance, and they would be real to them in whatever way things are real when they are the only version you have ever known. But something would be different. Something would be quieter and colder and more enclosed than the best of human civilization has tended to be when it had a sky to look at and a star to warm it. That much seems as certain as anything in this imagined world. The warmth of a star is not only thermal. It is not only the energy that keeps the surface temperature above freezing and the food chains intact and the water cycle moving. There is another kind of warmth that comes from having a sun, from waking up and knowing that the light is going to come back, that the day is going to begin, that the long dark of the night has an ending built into it, from the experience of standing in sunlight and feeling it on your skin, present and warm and immediate. From the sky being a place of depth and light rather than a ceiling of rock. All of that would be gone, and humanity, brilliant and adaptable and persistent as it is, would be poorer for the losing of it in ways that it might take generations to fully understand. Rest in that thought gently, not with grief, but with appreciation. The sky above you is still open. The sun will still rise. The warmth that falls on your face on an ordinary morning is not ordinary at all. It is the product of an almost incomprehensible chain of fortunate circumstances. And it is here, and it is real, and it is yours. There is a particular kind of loss that arrives not all at once but in layers. The first layer you notice immediately. It is large and obvious and demands your attention. But beneath it are other layers, quieter ones, things you did not think to grieve until you reached for them and found them gone. And beneath those, still more small things, almost trivial things, that turn out to carry an unexpected weight because of what they connected you to, what they meant without your ever having consciously assigned them meaning. The darkness we have been imagining tonight is that kind of loss. There are the enormous things. The warmth, the food chains, the surface world, the sky full of stars. We have spent time with those. But there are also the smaller things. The things that organized daily life. The things that told you where you were and when you were and what season it was and which direction was home. The things that were so woven into the fabric of ordinary existence that you would not think to list them among the things you depended on, until they were gone. Tonight we sit with some of those. The calendars, the navigational stars, the animals that knew where to go by reading the sky, the lights at the poles, the planets standing in the night like bright lanterns, the comets with their streaming tails, the photograph of a small, luminous, blue world, the observatories on their hilltops, full of instruments built for a universe that still had light in it. Each of these is a small story. Together they compose something larger, a portrait of just how deeply and in how many ways human civilization and the living world have always been organized around light, around the particular light of our particular star, in our particular corner of this particular galaxy. Around the assumption, so fundamental that it was never an assumption at all, that the light would keep coming. Let us begin with time. Human beings have been tracking time by the sky for as long as there have been human beings. Before clocks, before calendars in the modern sense, before writing, the sky was the clock and the calendar. The daily movement of the sun across the sky told you what hour it was. The moon's monthly cycle of waxing and waning gave you a unit of time longer than a day but shorter than a year, and virtually every ancient culture built some version of a monthly calendar around it. The yearly cycle of the sun, its rising and setting points moving north and south along the horizon as the seasons turned, the length of days growing and shortening in a reliable rhythm, gave agriculture its timing. Plant here, harvest there. The rainy season begins when this star rises at dawn. The floods come when that constellation appears above the eastern horizon. The great stone monuments of ancient civilizations are, among other things, calendars, precisely aligned to catch the first light of the solstice sunrise, or to frame the setting moon at a particular point in its cycle, or to track the annual journey of a specific star across the sky. The people who built these structures did not think of themselves as doing astronomy in the scientific sense. They were doing something more immediate. They were reading the sky to know when to plant and when to harvest, when to celebrate and when to prepare, when the world was in its right order and when it needed to be attended to. The sky was not a subject of study. It was a working tool, perhaps the most important one our ancestors had. All of that would end. Not the need for it, the need to organize time, to know when to do what, to coordinate human activities across seasons and years, but the sky-based infrastructure that had served that need for tens of thousands of years. Without the sun rising and setting, there would be no solar calendar. Without the moon cycling through its phases, reflecting the light of a star that no longer shone, there would be no lunar calendar. Without the stars appearing seasonally in their familiar patterns, rising in the east as the year progressed and moving through the sky in their ancient, reliable rhythm, there would be no stellar calendar. Time would not disappear. Human beings would still count days and years, still coordinate their activities, still maintain whatever social structures and schedules had survived the darkness. But the sky, which had been humanity's original timekeeper, would no longer be available for that role. The connection between the turning of the year and the movement of lights overhead, which every human culture in every corner of the world had built some version of, that connection would be broken. Another thread cut between human life and the astronomical world it had always been embedded in. The navigational consequences would be equally profound, and they stretch back just as far. For most of human history, the ability to navigate across the open ocean depended on the stars. Not entirely, currents and swells and the behavior of birds and the color of the water all played their roles in the extraordinary navigational traditions of cultures like the Polynesians, who crossed thousands of miles of open Pacific in canoes using methods that combined every available signal. But the stars were central. The North Star, sitting almost directly above the Earth's North Pole, was a fixed point in the sky around which everything else appeared to rotate, a constant reference that told you your latitude in the Northern Hemisphere simply by measuring its height above the horizon. The Southern Cross served a similar orienting function in southern skies. The rising and setting points of specific stars told you your direction of travel. The height of certain stars above the horizon told you how far north or south you were. The entire era of European maritime expansion, the age of exploration, the opening of trade routes, the connecting of continents, was built on the back of stellar navigation. Every ship that crossed the Atlantic or rounded the Cape or made the passage to the East Indies was guided, at least in part, by the same stars that guided every previous navigator in every previous era. The stars were not a navigational aid in the sense of something optional, something that supplemented more reliable methods. For centuries, they were the method, the thing that made open ocean travel possible at all, rather than a terrifying leap into a directionless void. In a world with a dark sky and no visible stars, those traditions would be severed. The knowledge would survive, perhaps, in books and archives, descriptions of how the old navigation worked, records of the star positions that no longer existed to be observed. But the practice would be impossible. You cannot navigate by a star you cannot see. The dark sky above a frozen ocean would offer nothing to a navigator seeking a bearing, nothing to tell them which way was north or how far they had come or what direction home was in. The tools of celestial navigation, sextants and star charts and nautical almanacs would become artifacts, historical curiosities, instruments built for a universe that used to work differently. And it is not only human navigators who would lose their way. The living world has its own navigators, and they too have always read the sky. The birds that migrate thousands of miles between breeding and wintering grounds, crossing oceans and mountain ranges and deserts without maps, navigating partly by the stars. They would be lost. The European robin, the American warbler, the Arctic tern making its extraordinary annual journey from pole to pole. These creatures carry within them the ability to read the night sky, to use the pattern of stars as a compass, to orient themselves by the rotation of the celestial sphere around the pole. Take the stars away and that compass is gone. The sea turtles that navigate across entire ocean basins, returning after decades to the exact beach where they were born, guided partly by the Earth's magnetic field and partly by celestial cues, they too would find their navigational systems disrupted. The moths and other nocturnal insects orient themselves by the moon's position, using it as a distant fixed reference to maintain a straight course, no moon, no reference. The remarkable migrations that move billions of animals across the face of the Earth every year, redistributing life and energy from one hemisphere to another in a cycle as old as the animals themselves, would be thrown into confusion by the loss of the sky's familiar landmarks. This matters not just for the animals individually, but for the ecosystems that depend on those migrations. The fertilization of ocean feeding grounds by the movement of nutrients carried by migrating creatures. The pollination is carried out by insects moving between flowering plants guided by light cues. The seed dispersal is accomplished by migrating birds. All of these are connections in a web of interdependence that the living world has spent millions of years constructing, and many of the threads of that web are tied, ultimately, to the light of the sky. Look toward the poles. In this imagined dark world, and notice another absence. The auroras, those extraordinary curtains and ribbons of colored light that appear near the Arctic and Antarctic on clear nights, flickering green and purple and red and white across the sky, one of the most genuinely otherworldly things a person can witness on Earth, are powered by the sun in a way that is different from the direct illumination we have been talking about. They are not reflected sunlight, not the sun's heat, not the sun's gravitational influence. They are the product of the sun's activity in a more dynamic sense. The stream of charged particles that flows continuously outward from the sun in all directions, the solar wind, which is deflected by Earth's magnetic field and funneled toward the poles, where it interacts with the upper atmosphere and causes the gases there to emit light. Without the sun, the solar wind stops. The continuous stream of charged particles ceases. The Earth's magnetic field still exists. It is generated by the planet's own internal dynamics and does not require the sun. But without particles to funnel and excite, it produces no aurora. The polar skies, which on active nights are among the most spectacular displays in nature, would go dark and still. Another light removed from the sky. Another feature of the living Earth that turned out to depend, in one way or another, on that single medium-sized star. Now let the imagination travel outward from Earth, into the rest of the solar system. Let it visit the planets we have always known as the bright wanderers, the objects that move against the fixed background of the stars and have fascinated skywatchers since the first human beings noticed that some lights in the sky moved and some did not. Jupiter, Saturn, Mars, Venus, the outer giants Uranus and Neptune. These worlds, so different from each other in size and composition and distance, share one thing in our sky. They shine. They are visible. Some of them are among the brightest objects in the night sky, rivaling the brightest stars, moving slowly through the constellations in their longer, more stately cycles. Saturn can be seen with the naked eye, a steady golden point, and even a modest telescope reveals its extraordinary ring system, that flat, gleaming disk of ice and rock encircling the planet, visible across hundreds of millions of miles of space, one of the most immediately beautiful things a first-time telescope user ever sees. In a galaxy without starlight, the planets go dark. They are not self-luminous, they produce no light of their own, at least not in visible wavelengths. Every photon that reaches your eye when you look at Jupiter or Saturn is a photon that began its journey at the sun, traveled outward to the planet's surface or cloud tops, bounced off, and then traveled back inward toward Earth. Without the sun, there are no photons to bounce. The planets become invisible, not just dimmer, but genuinely, completely invisible to the naked eye. The golden disk of Saturn, the banded clouds of Jupiter, the reddish gleam of Mars, all gone, replaced by invisible dark worlds moving silently through a dark system, present but undetectable without instruments sensitive to other wavelengths. And Saturn's rings, those billions of icy fragments ranging from dust grains to house-sized boulders, arranged in a flat disk that spans hundreds of thousands of kilometers, would vanish from view along with everything else. Their beauty, which has stopped people at telescopes in their tracks for centuries, depends entirely on sunlight catching them at the right angle, sparkling off the ice, creating that sense of impossible delicacy and precision. Without sunlight, the rings are still there, still orbiting, still spread in their flat mathematical perfection around the planet. But they cannot be seen. They become a structure that exists only in scientific records and human memory, their geometry real but their appearance impossible. The comets would be similarly transformed. These travelers of the outer solar system, irregular chunks of ice and rock and dust on long elliptical orbits that occasionally bring them swinging close to the sun, are, for most of their existence, invisible and inert. Cold, dark objects drifting through the outer solar system, indistinguishable from any other piece of space debris. What transforms a comet into the spectacular sight it can be, the bright coma surrounding the nucleus, the long glowing tail streaming away from the sun for tens of millions of kilometers, is heat. Sunlight reaching the comet as it approaches the inner solar system warms its surface, vaporizing ices and releasing trapped gases and dust, which spread out around the nucleus and are then pushed back by the solar wind to form that characteristic tail. The comet becomes visible, becomes dramatic, becomes the kind of object that has historically filled sky watchers with wonder and dread, precisely because sunlight is acting on it. Without sunlight, comets lose their tails. The ices stay frozen. The gas stays trapped. The comet passes through the inner solar system as dark and silent and inert as it was in the outer reaches. No coma, no streaming queue, just a dark object on a curved trajectory, invisible without specialized instruments, unannounced, unremarkable. There is a photograph taken in 1990 that sits among the most quietly significant images ever made. A spacecraft had traveled to the edge of the solar system and turned its camera back toward the center. In the image, against the black of space, is a pale blue dot, barely a pixel across, a tiny speck of blue suspended in a beam of scattered sunlight. The Earth, our world, seen from a distance of about 6 billion kilometers, so small that it barely registers, so faint that it almost disappears into the background. What made that image possible and what gives it its particular quality, the paleness, the blueness, the faint shimmer of it, is sunlight. The Earth in that photograph is lit by the sun, its oceans and atmosphere scattering the sun's light in ways that produce that characteristic blue color. The image is not just of the Earth. It is of the Earth in sunlight. The sun is, in a sense, in the photograph too, invisible, off-frame, but present in every photon that made the image possible. In a dark galaxy, that photograph could not be taken. The Earth seen from 6 billion kilometers away would not be a pale blue dot. It would be nothing, an invisible object in an invisible system, indistinguishable from the empty space around it. The particular beauty of that image, which for many people carries an almost philosophical weight, a reminder of how small and fragile and improbable our world is, depends on the light. Remove the light and the image becomes impossible, and with it, that particular perspective on our own smallness. That specific kind of humility. The instruments built to study the sky would follow everything else into obsolescence. The great observatories, perched on their mountaintops and remote plateaus, their domes containing mirrors ground to extraordinary precision, designed to collect and focus the faintest traces of light from the most distant corners of the observable universe, were built on an assumption so fundamental that no one who designed them ever thought to articulate it. That there would be light to collect. That the universe would continue to produce photons. That pointing a sufficiently large and precise mirror at the sky would always yield something to see. In a galaxy without stars, the observatories would stand empty. Their mirrors are still polished. Their mounts are still capable of tracking across the sky with extraordinary precision. Their computers are still running, waiting for signals to process. But there would be nothing to point at. The sky above, even a perfectly clear, perfectly transparent sky, would offer nothing to an instrument built to gather visible light. Other wavelengths might still carry information. Radio waves from pulsars, gravitational waves from distant mergers, the cosmic microwave background from the beginning of the universe, still propagating through space, indifferent to the local darkness of our galaxy. But the tradition of visual astronomy, of grinding mirrors and focusing starlight and spending nights in cold domes watching the sky turn overhead, would be over. The observatories would become monuments, museums of a practice that had been possible for as long as there were eyes to look up, and that had ended quietly and completely along with the light that made it possible. There is something both melancholy and beautiful in that image. The observatory on its mountain, dome open, mirror pointed at an empty sky. The instrument is still perfect, still capable technically of doing what it was made to do. The only thing missing is the thing it was built to receive. The light that, for billions of years, poured out from billions of stars in all directions, filling the galaxy with photons, making the universe something that could be seen and studied and wondered at. All of these things, the calendars and the navigational stars and the migrating animals and the auroras and the planets and the comets and the photographs and the observatories, were not separate losses. They were expressions of a single underlying fact, that life and civilization on this planet, in every dimension, had grown up in the light, had shaped itself around the light, had taken the light as its starting point, its given condition, the thing that was always present and always reliable and did not need to be thought about because it had never not been there. To lose it is to lose the ground everything was built on. Not just the warmth and the energy, those are the physical foundations, but the cultural foundations too. The orientation, the sense of being in a place with a sky that could be read, in a time that could be marked by the movements of lights overhead, in a world where beauty arrived without being arranged, where the day had a shape defined by light, where migration routes and ocean crossings and the timing of harvests were written in the stars. All of it written in the stars. All of it legible as long as the stars were there. Breathe slowly. Feel the weight of the dark world we have been imagining lift a little. The stars are still there tonight. They will be there tomorrow night and the night after for billions of years to come. The auroras are still flickering at the poles. Saturn's rings still gleam in the cold sunlight, waiting for anyone patient enough to point a telescope and look. The sea turtles still know where they are going. The birds still read the sky. The light has not gone anywhere. It is still here, still falling, still making all of this possible. Imagine for a moment a galaxy that still exists but can no longer be seen. The Milky Way, stretched across hundreds of thousands of light years of space, suddenly invisible to the universe around it. This is the paradox of darkness we're exploring tonight, where absence of light does not mean absence of existence. Even though the galaxy looked dark, the stars themselves could still physically exist. They might simply stop producing light, turning the Milky Way into a giant, invisible structure drifting through space. Think about that for a moment. Billions upon billions of stellar bodies. Still there, still massive, still real, but producing no light whatsoever. Like a city where every single light has been switched off, yet all the buildings, all the streets, all the structures remain exactly where they've always been. The Milky Way would become a ghost of itself, a phantom galaxy, unseen but undeniably present in the cosmic fabric of space. From the outside, other galaxies would look toward our corner of the universe and see nothing. Where once a magnificent spiral of stars blazed across the darkness, there would be only empty space, or so it would appear. But appearance and reality are not always the same thing. A dark Milky Way would still contain enormous amounts of gravity. Stars, planets, black holes, and dark matter would continue orbiting invisibly through space. Gravity, you see, doesn't need light to function. It is one of the fundamental forces of the universe, and it operates whether we can see its source or not. Every star that went dark would still possess the same mass it had when it was shining. Every planet would still pull on its neighbors with the same gravitational embrace. Every black hole would still warp the fabric of space-time around it. The orbital dance would continue. Planets would still circle their dark suns. Moons would still trace their paths around invisible worlds. Binary stars would still spiral around each other in the darkness, their gravitational partnership unchanged by the absence of light. If you could somehow map the gravity of the Milky Way, trace every gravitational field, every mass, every pull and tug across hundreds of thousands of light years, you would see the galaxy still there, still structured, still organized into its beautiful spiral arms, even though those arms would be invisible to any telescope. And there's something else that would remain. Even if the galaxy became visually dark, invisible dark matter would still make up much of the Milky Way's total mass, silently shaping the motions of everything inside it. Dark matter, one of the universe's greatest mysteries. We cannot see it. We've never directly detected it. We only know it exists because of how it affects the things we can see. Or in this case, the things we could once see. Scientists estimate that dark matter makes up roughly 85% of all matter in the universe. In the Milky Way, this invisible substance forms a massive halo around the visible galaxy, or what used to be the visible galaxy. It provides the gravitational scaffolding that holds everything together, preventing the outer regions of the galaxy from flying apart as they spin through space. In a dark Milky Way, dark matter would become even more important. It would be the dominant form of matter by far, with the once bright stars now joining it in invisibility. The galaxy would become a realm ruled almost entirely by things we cannot see, governed by forces that operate in silence and shadow. And yet, the structure would persist. The dark matter halo would continue embracing the galaxy. The gravitational wells it creates would still channel the movement of stars and gas clouds. Nothing about its function would change, only our ability to witness the light that once revealed its presence. Even in total darkness, gravity from the Milky Way would continue holding the solar system in orbit around the galactic center, completing one galactic rotation roughly every 230 million years. Our solar system is on a journey. Right now, as you rest and let these words wash over you, we are moving through space at approximately 514,000 miles per hour. We are orbiting the center of the Milky Way, following a path that takes us around the entire galaxy once every 230 million years or so. This is called a galactic year, or a cosmic year. The last time our solar system was in this position in its orbit, dinosaurs were just beginning to emerge on Earth. The next time we complete a full orbit, hundreds of millions of years will have passed, and Earth, if it still exists, will be unrecognizably different. In a dark Milky Way, this journey would continue. The sun, now dark and cold, would still possess its mass. The planets would still orbit around it, and the entire solar system would still be held in the gravitational grip of the galaxy, tracing that same ancient path through space. We would still be moving even if we could no longer see where we were going, still orbiting the galactic center, even if that center produced no light to guide us. The cosmic clockwork would tick on, invisible but inexorable, measuring out galactic years in the darkness. And at the heart of it all, something even more mysterious would wait. The Milky Way's supermassive black hole, Sagittarius A*, would remain hidden in the darkness unless astronomers detected its gravitational pull on nearby objects. At the very center of our galaxy sits a monster, a supermassive black hole with a mass of roughly 4 million times that of our Sun, compressed into a region of space smaller than the orbit of Mercury. We call it Sagittarius A*, and it is one of the most extreme objects in the known universe. Even now, with the galaxy still shining, Sagittarius A* is invisible. Black holes, by their very nature, emit no light. Nothing can escape from beyond their event horizons. Not matter, not energy, not even light itself. We only know Sagittarius A* exists because we can watch stars orbiting around it, tracing paths around an invisible gravitational anchor. In a dark galaxy, this wouldn't change. The black hole would still be there, still massive, still pulling everything nearby into its gravitational embrace. But now, without the light from orbiting stars to reveal its presence, it would be even more hidden. A dark spot in a dark galaxy, a void within a void, yet its influence would remain. If any matter drifted too close, it would still be pulled in. If any invisible star passed nearby, its path would still be bent by that tremendous gravity. Sagittarius A** would still rule the galactic center, a hidden throne for an invisible empire. And it wouldn't be the only black hole in the darkness. Even in total darkness, black holes inside the Milky Way could still remain active. Matter falling into them might continue releasing X-rays and radiation, creating faint pockets of deadly energy in the dark galaxy. Black holes are not always quiet. When matter falls into them, dust, gas, the remnants of dead stars, it doesn't simply disappear. First, it spirals inward, forming what's called an accretion disk. As the matter in this disk compresses and heats up from friction and gravitational forces, it can reach temperatures of millions of degrees. At these extreme temperatures, the matter emits powerful radiation, X-rays, gamma rays, intense bursts of energy that can be detected from thousands of light years away. This is how we find many black holes. Not by seeing the black holes themselves, but by detecting the violent death cries of matter falling into them. In a dark Milky Way, this process could continue. Even without stars, there would still be gas clouds, dust, debris from dead worlds. If any of this material drifted too close to a black hole, it would be drawn in, and in those final moments before crossing the event horizon, it would shine. Not with visible light, perhaps, but with high-energy radiation. So scattered throughout the dark galaxy, there might be pockets of invisible energy. Regions where X-rays and gamma rays flood the darkness, deadly to any hypothetical life that might exist, but undetectable to human eyes. The galaxy would be dangerous in ways we couldn't see, its threats hidden until the moment they struck. Though perhaps a few things would remain visible, the glowing tails of ionized gas around some black holes and neutron stars might become some of the only visible sources of energy left in the galaxy. In some systems, the story isn't quite over when matter falls toward a black hole or neutron star. Sometimes powerful magnetic fields channel some of that infalling matter into jets, streams of particles and energy that shoot out from the poles of these extreme objects at nearly the speed of light. These jets can ionize the gas around them, causing it to glow. The light is often faint, but it's there. In our current galaxy, these glowing regions are usually washed out by the light from nearby stars, barely noticeable against the brilliant backdrop of the Milky Way. But in a dark galaxy, they might become beacons. Tiny points of light in the overwhelming darkness. An observer with sensitive enough instruments might see them scattered across the invisible galaxy like fireflies on a moonless night, rare, faint, but precious evidence that energy and activity still existed in the void. These glowing tails would trace the positions of some of the galaxy's most extreme objects. Each faint glow would mark a place where gravity had grown strong enough to tear matter apart, where space-time itself was bent into extreme curvature. They would be monuments to the power that still lurked in the darkness. And there would be other signals, too, though harder to detect. Even after visible light vanished, some dead stars called neutron stars could still emit invisible radio pulses, quietly flashing through the darkness like hidden galactic lighthouses. When a massive star dies in a supernova explosion, its core can collapse into something extraordinary. A neutron star. These objects pack more mass than our sun into a sphere only about 12 miles across. They are so dense that a teaspoon of neutron star material would weigh about 1 billion tons on Earth. Many neutron stars spin rapidly, completing dozens or even hundreds of rotations per second. And as they spin, they emit beams of radio waves from their magnetic poles. If these beams happen to sweep past Earth, we detect them as pulses, regular, rhythmic flashes of radio energy. We call these objects pulsars. In a dark Milky Way, pulsars would continue their lighthouse routine. They wouldn't produce visible light, but their radio pulses would still flash through space, invisible to the eye but detectable with the right instruments. Each pulse would be like a heartbeat, evidence that the galaxy, though dark, was not dead. These radio signals would travel through the darkness, crossing empty light years, carrying information about the extreme physics occurring at their source. To any civilization with radio telescopes, these pulses would be messages from the void, proof that structure and order still existed in the absence of light. And waiting in that darkness would be the materials of future stars. Massive clouds of cold hydrogen gas would continue drifting through the Milky Way invisibly, waiting for conditions that might someday allow stars to form again. Hydrogen is the most abundant element in the universe, and it fills the space between stars. In vast clouds called nebulae, this hydrogen can become dense enough that gravity begins to pull it together. Given enough time and the right conditions, these clouds collapse, heat up, and eventually ignite, forming new stars. In a dark Milky Way, these hydrogen clouds would still exist. They would drift through the darkness, invisible and silent, containing within them the potential for future light. Each cloud would hold enough material to create thousands or even millions of stars, if only the conditions were right. But conditions might not be right. Without existing stars to trigger the collapse of these clouds, without supernovae to compress them with shock waves, they might simply drift forever, waiting, patient, holding the memory of what the galaxy once was and the promise of what it might someday become again. These clouds would be like seeds scattered in a dark garden, seeds that might never germinate, but that carry within them all the information needed to grow. In the cold and dark, they would preserve the possibility of light, a possibility that might remain unrealized for billions upon billions of years. And there would be other clouds too, even more mysterious. Giant molecular clouds inside the galaxy would remain hidden in darkness, silently drifting for millions of years between invisible stars. Molecular clouds are the densest regions of the galaxy, thick with not just hydrogen but also more complex molecules. Carbon monoxide, ammonia, water, even organic compounds. These are the stellar nurseries, the places where stars are born. In our current galaxy, they are vast and dark even now, visible only when backlit by more distant stars or when young stars forming inside them begin to glow. In a dark Milky Way, these molecular clouds would be completely hidden. Vast structures, some of them hundreds of light years across, drifting through space like invisible continents. They would contain enough matter to form hundreds of thousands of stars, but without a trigger to start the collapse, they might simply drift unchanged for eons. Inside these clouds, chemistry would continue. Molecules would form and break apart. Cosmic rays would ionize atoms. Complex organic compounds might continue building up over millions of years, becoming more intricate even though no light would ever illuminate them. These clouds would be patient. They would drift through the dark galaxy, carried by galactic rotation, occasionally passing through the spiral arms where they would experience slight gravitational compression, but perhaps not enough to ignite star formation. They would be repositories of potential, archives of the materials needed to build new worlds, waiting for a spark that might never come. And so the invisible galaxy would exist, full of structure, full of matter, full of gravity and motion and the memory of light. A ghost of what once was, drifting through the cosmos, present but unseen, real but invisible. In the darkness, the Milky Way would continue its ancient journey through space, patient and silent, carrying within it all the pieces needed for light to return, if the universe ever chose to ignite them again. Close your eyes for a moment and imagine looking up at the night sky. Not the sky as it is now, filled with stars and the glowing band of the Milky Way, but a sky of pure, unbroken darkness. No points of light, no constellations, no distant glow, just emptiness. This is what we're exploring now. A universe where light has left us, where the very fabric of the night sky has changed in ways that would challenge everything we understand about our place in the cosmos. In the darkness, the Milky Way's spiral shape would become nearly impossible to detect with ordinary vision, hiding the true structure of our galaxy from most observers. Right now, when we look at images of our galaxy from the outside, those beautiful photographs taken by space telescopes, showing the elegant spiral arms stretching across hundreds of thousands of light years, we're seeing structure revealed by light. Each spiral arm is outlined by young, bright stars. Each band of darkness between them shows where dust blocks the light from stars beyond. The spiral shape of the Milky Way is one of its most defining features. Those great curved arms, sweeping around the galactic center like water swirling down a drain. They tell us about the history of our galaxy, about how gravity and rotation have shaped the matter within it over billions of years. But in a dark galaxy, that structure would vanish from sight. The spiral arms would still be there, still containing billions of invisible stars, still maintaining their shape through gravity. But without light to trace them, they would become impossible to map with ordinary telescopes. The grand design of our galaxy would be hidden, locked away in darkness. An observer in another galaxy looking toward the Milky Way would see nothing. Where once there was a magnificent spiral of light, there would be only a dark patch of sky. The structure would remain, but the signature that revealed it would be gone. Our galaxy would become architecturally invisible, and there would be other things that faded from view as well. The cosmic dust spread throughout the galaxy would become harder to detect because dust clouds are usually seen by the way they reflect or block starlight. Dust sounds so simple, so mundane, but cosmic dust is everywhere in the galaxy. Tiny grains, each one smaller than a particle of smoke, but scattered by the trillions upon trillions throughout interstellar space. Some of it is ancient remnants from the formation of the galaxy itself. Some of it is new, cast off by dying stars, forged in the violence of supernovae. We see this dust because of how it interacts with light. Sometimes it reflects starlight, creating beautiful reflection nebulae that glow with soft, ethereal blues. Sometimes it blocks starlight, creating dark patches and lanes that snake through the brighter regions of the Milky Way. Some of the most famous photographs of our galaxy show these dark dust lanes, silhouetted against the glow of millions of stars behind them. In a dark Milky Way, there would be no starlight to reflect, no background glow to silhouette against. The dust would still be there, still filling the spaces between invisible stars, still forming clouds and filaments and complex structures. But it would be as dark as everything else. The dust would become a hidden component of the galaxy, detectable only through its gravity or perhaps through the way it absorbed radiation in non-visible wavelengths. The texture it once gave to the night sky would be erased. The intricate patterns it created would be lost to the darkness. And with the dust invisible, other beauties would fade too. Gas clouds and nebulae inside the galaxy would also fade from view because most of their beautiful colors are created by nearby stars energizing the surrounding gas. Think of the images you've seen of nebulae. The Orion Nebula with its swirling reds and pinks. The Eagle Nebula with its famous pillars of creation. The Carina Nebula with its golden dust and bright blue stars. These are some of the most stunning sights in the entire galaxy, vast clouds of gas and dust glowing with vibrant colors, each one a masterpiece of cosmic art. But those colors don't exist on their own. They are created by a process called ionization. Hot, young stars embedded in or near the nebulae emit intense ultraviolet radiation. This radiation strikes the atoms in the surrounding gas, stripping away electrons and energizing what remains. When those atoms recapture electrons, they emit light at specific wavelengths: red for hydrogen, green for oxygen, blue for helium. The nebulae glow because stars make them glow. They are painted by starlight. In a dark Milky Way, there would be no young stars to energize the gas. No ultraviolet radiation to ionize the atoms. The nebulae would still exist as vast clouds of gas and dust, but they would be completely dark, silent, invisible. All those colors, the reds and pinks and blues and golds that make nebulae so breathtaking, would vanish. The universe would lose an entire category of beauty. These clouds would drift through space as dark as the void around them, their presence revealed only by the absence of other things, by the gravitational effects they produced, by the void they created in any background radiation. The gallery of the galaxy would go dark. The cosmic art would be locked away where no one could see it. And without these landmarks, space itself would feel different. Space would feel visually flatter to human observers because stars help provide depth and orientation in the night sky. When you look up at the night sky, you're seeing depth. Some stars are relatively close, just a few light years away. Others are thousands or even tens of thousands of light years distant. The variation in brightness, the way some stars appear to cluster while others stand alone. All of this gives us a sense of three-dimensional space stretching away from us in all directions. Constellations help us orient ourselves. Sailors once navigated by the stars. Travelers used them to find their way. Even now, stargazers learn to hop from one constellation to another, building a mental map of the sky. But in a dark galaxy, all of that would be gone. There would be no bright stars and dim stars, no sense of some things being closer and others farther away. There would be no constellations to mark your position, no familiar patterns to guide your eye. Space would feel flat, empty, without dimension, like staring at a perfectly blank wall in a dark room, where you can't tell if the wall is 10 feet away or 100. For a human observer, perhaps an astronaut on a long mission through the darkness, or a colonist on a world circling an invisible sun, the psychological impact would be profound. We are used to the sky having structure, having landmarks, having points of reference. Take all of that away, and space would feel alien in a way it never has before. The cosmos would become featureless, directionless, a void without variation. And in that void, our understanding of reality itself might shift. The Milky Way's darkened state could make the universe appear much emptier to observers, even though countless unseen objects would still surround them. Imagine being an astronomer in a civilization that arose after the galaxy went dark. You would point your optical telescopes at the sky and see almost nothing, perhaps a few distant galaxies, if they were still producing light. Perhaps some faint background glow from the cosmic microwave background. But no stars, no Milky Way, no local universe filled with light and motion. You might conclude that your civilization was alone, that your world was a rare island in an empty ocean of space. You might develop a cosmology based on emptiness, on isolation, on the idea that the universe is mostly void with only scattered specks of matter. And you would be wrong, completely, utterly wrong. All around you would be billions of stars, planets, moons, asteroids. You would be sitting in one of the densest regions of matter in the entire universe, a galaxy. But you wouldn't know it. You couldn't see it. The true nature of reality would be hidden from you by darkness. You would build your understanding of the cosmos on what you could observe, and what you could observe would be a lie. Not a deliberate lie, but a lie by omission. The universe would be withholding its secrets. This is one of the most unsettling aspects of a dark Milky Way. It wouldn't just hide things. It would create false impressions. It would make the rich appear poor, the full appear empty, the crowded appear sparse. Truth would require tools beyond vision. It would require gravity measurements, radio telescopes, X-ray detectors, instruments that could sense what the eye could not. And even then, you would need to believe that there was something there to detect in the first place. And for those who remembered the light, the change would be devastating. If all stars stopped shining at once, Many civilizations across the galaxy might mistake the event for the end of the universe itself. Consider a civilization on a planet orbiting a normal star in a normal stellar neighborhood. For millions of years, perhaps billions, they look up at a sky filled with stars. They study astronomy. They map the heavens. They send their first tentative probes into space, perhaps even establish colonies on nearby worlds. And then one day, or perhaps over the course of years or decades, the stars begin to go out. One by one, or in great swaths across the sky, the familiar lights vanish. The constellations disappear. The Milky Way fades away, until finally, their own sun dims and dies, and their world is plunged into darkness and cold. How would they interpret this? What would they think was happening? Many might believe it was the end of everything, a cosmic apocalypse. The heat death of the universe arrived all at once. They might have prophecies or religious texts that predicted such an event. They might have scientific theories that, however wrong, seemed to explain what they were witnessing. They would likely not guess the truth, that the stars still existed, still orbited the galactic center, still maintained their mass and gravitational pull, that the universe hadn't ended, but had simply changed state, that existence continued, just without light. The psychological and cultural impact would be immense. Entire civilizations might collapse in panic. Others might retreat into themselves, believing there was nothing left beyond their own darkening world. Some might continue their science, desperately trying to understand what had happened, even as their instruments lost the ability to observe the distant universe. It would be a galaxy-wide trauma, an existential crisis on a scale that's almost impossible to imagine. And the emotional weight of that darkness would affect everyone. The silence of a dark galaxy could feel overwhelming to future explorers, as most familiar visual signs of life and activity in space would be gone. Space, as they say, is already silent. Sound doesn't travel through vacuum. But when we think of space as alive, as active, as full of interesting things, we're really thinking about light. We see stars. We see planets reflecting sunlight. We see galaxies glowing in the distance. We see nebulae and comets and auroras. Light is how space communicates with us. It's how the universe says, I'm here, I'm active, I'm doing interesting things. In a dark galaxy, that communication would stop. Future explorers, if such beings could exist in a universe without light, would travel through what felt like an empty void. Their ships would move between invisible waypoints. They would navigate by instruments alone, never by sight. There would be no glowing destination ahead of them. No sun grew brighter as they approached. No planet caught the light as they drew near. Just darkness ahead, darkness behind, darkness in all directions. The isolation would be profound. Even knowing intellectually that stars and planets and other objects surrounded them, the absence of any visual confirmation would create a sense of overwhelming loneliness. Space would feel dead, even though it was full of matter and motion. Some explorers might struggle with this psychologically. The human brain, or whatever equivalent consciousness existed, is adapted to use vision as a primary sense. Take that sense away, make it useless, and part of the mind might rebel. Anxiety, depression, claustrophobia, even in the openness of space. These could all become hazards of travel in a dark galaxy. The universe would become a sensory deprivation chamber on a cosmic scale. And the darkness would change not just how space felt, but what it meant. The absence of starlight would make space travel emotionally unsettling, as astronauts drifting between planets would see almost no glowing destinations ahead of them. Think about the Apollo missions. Astronauts leaving Earth orbit, traveling to the moon. They could look back and see Earth behind them, that famous pale blue, beautiful and fragile against the darkness. and they could look ahead and see the moon growing larger, its surface illuminated by the distant sun, a destination that they could watch approaching. The journey had visual feedback. They could see where they came from and where they were going. Now imagine making the same journey in total darkness. You launch from an invisible Earth, orbiting an invisible sun. You travel through space where you can see nothing, and you're heading toward a moon that produces no light, orbiting a planet that produces no light, in a solar system lost in the greater darkness of the galaxy. You would have to trust your instruments completely. Your radar, your gravitational sensors, your navigation computers. They would tell you that you're on course, that your destination is ahead, that you're going to arrive safely. But you would see none of it. You would be flying blind in the most literal sense possible. The psychological challenge would be immense. Humans are visual creatures. We trust what we can see. Taking away that sense, forcing us to rely entirely on instruments and calculations. It would require a different kind of courage, a different kind of faith. Some astronauts might not be able to do it. The emotional weight of traveling through complete darkness, with no visual confirmation of where they were or where they were going, might be too much. Space travel would require not just technical skill, but psychological resilience of a kind we've never had to develop before. The universe would test us in new ways, challenge us to trust what we cannot see, force us to believe in destinations we can never witness until we arrive. And throughout the galaxy, countless worlds would share this darkness. Some rogue planets already drift through the universe without stars, and a dark Milky Way could make billions more worlds resemble these lonely wandering planets. Right now, scattered through the galaxy, there are planets that orbit no star. Rogue planets, wandering worlds. They formed in solar systems long ago, but were ejected by gravitational interactions. Too close an encounter with another planet, the death of their parent star, some cosmic accident that sent them tumbling out into interstellar space. These worlds drift alone through the darkness. They receive no warmth from a sun. Their surfaces are frozen, locked in eternal night. If they have atmospheres, those atmospheres might be frozen too, lying on the surface as layers of solid nitrogen and oxygen and carbon dioxide. These are dead worlds in a way that few other places in the universe are dead. In a dark Milky Way, billions of planets would suddenly resemble these rogues. Worlds that had orbited warm, bright stars would find themselves circling invisible stellar corpses. They would still be in orbit, still bound by gravity to their dark suns, but in every other way that matters, they would be as isolated as the rogues. The transformation would be sudden and complete. One moment, a planet bathed in light and warmth. The next plunged into cold and darkness. Any life that existed would face immediate extinction unless it could somehow adapt or retreat into protected environments. And from the perspective of an observer, these worlds would become impossible to distinguish from true rogue planets. They would be dark shapes in the darkness, invisible unless you happened to pass very close or detected them through their gravitational influence. The galaxy would become populated by ghost worlds. Planets that still existed, still maintained their orbits, still held whatever geological processes their internal heat allowed, but were as isolated and unreachable as if they'd been cast out into intergalactic space. And in the end, looking at the galaxy from outside, over billions of years, a completely dark Milky Way could resemble a ghost galaxy, still full of mass and motion, but almost invisible against the universe around it. From a distance, from another galaxy looking toward our corner of the universe, the Milky Way would simply vanish. Where once there was a spiral of light, one of the grand structures of the local universe, there would be nothing. Just empty space, or what appeared to be empty space. The galaxy would become a ghost, present but unseen, real but invisible, still containing hundreds of billions of stars, still maintaining its beautiful spiral structure, still rotating around its center once every few 100 million years, but offering no evidence of its existence to casual observation. It would be a cosmic magic trick, a vanishing act on a galactic scale. The Milky Way would still be there, still influencing its neighbors through gravity, still occupying its place in the local group of galaxies. But visually, it would be gone. And perhaps that's the most unsettling thing about a dark galaxy. Not that it would cease to exist, but that it would continue existing while being invisible. That all the structure, all the mass, all the billions of worlds and trillions of objects within it would persist, but silently, secretly, hidden behind a veil of darkness that no ordinary light could penetrate. The universe would carry on, but it would carry on in shadow. The Milky Way would become a memory, a ghost, a presence felt but not seen. And in that darkness, in that invisible continuation of existence, there would be a kind of strange peace. The galaxy would drift through space, patient and silent, keeping its secrets, waiting for a time, if such a time ever came, when light might return and reveal it once again. Science is built on observation, on measuring, on detecting patterns in nature and using them to understand how the universe works. For thousands of years, humanity has studied the cosmos by looking up at the night sky and watching the light that reaches us from distant places. But what happens when that light goes away? When the primary tool we've used to understand the universe, our ability to see, suddenly becomes useless. This is the challenge we explore now. The question of how we would continue doing science in a universe that has gone dark. Telescopes that rely on visible light would suddenly become far less useful. Astronomers would need to depend on radio waves, infrared signals, gravitational effects, and other invisible forms of detection. Think of all the great observatories humanity has built, the towering domes housing massive mirrors that gather faint starlight. The Hubble Space Telescope, orbiting above Earth's atmosphere, capturing images of distant galaxies in stunning clarity. The new generation of telescopes with mirrors dozens of feet across, capable of seeing planets around other stars. All of these instruments work by collecting light, visible light mostly, the same kind of light that human eyes can see. They're essentially giant eyes, gathering photons that have traveled across space for years or centuries or millennia, focusing them into images we can study and measure and learn from. In a dark galaxy, all of these telescopes would suddenly become almost useless. Oh, they might still detect a few things. Distant galaxies beyond the Milky Way, perhaps, if those galaxies were still producing light. Maybe some faint glow from the cosmic background. But the local universe, our own galaxy, the stars and nebulae and planets that make up our cosmic neighborhood, all of that would vanish from their view. Astronomy would have to transform. It would have to shift away from visible light and embrace other forms of radiation. Radio waves that pass through space even without stars. Infrared radiation that warm objects emit. X-rays from extreme cosmic events. Gravitational waves from colliding black holes and neutron stars. The tools would have to change. The methods would have to evolve. Astronomy would become less about seeing and more about detecting, about using instruments to sense things that human eyes could never perceive, even when those things were bright. It would be a revolution in how we study the cosmos, a new astronomy for a dark age. And some tools would become more important than ever before. Radio astronomy could become the dominant way of studying the universe because radio waves can still travel through space even without visible starlight. Radio waves are everywhere in the universe. They're emitted by pulsars spinning in the remnants of dead stars. They're produced by matter falling into black holes. They stream from the center of the galaxy where Sagittarius A* lurks. They even come from cold clouds of hydrogen gas. marking out the structure of the Milky Way's spiral arms. Right now, radio astronomy is important, but it's just one tool among many. Astronomers use it to complement optical observations, to see things that visible light can't reveal, to peer through dust clouds that would otherwise block their view. In a dark galaxy, radio astronomy would become essential. It might be the primary way, perhaps the only reliable way, to map the structure of the Milky Way. Radio telescopes would detect the pulses from neutron stars, using them as beacons to triangulate positions. They would sense the radio emissions from active black holes. They would map the distribution of hydrogen gas throughout the galaxy. The Great Radio Telescope arrays, dishes spread across continents, linked together to create instruments effectively the size of Earth, would become our eyes. They would see the invisible translated into data, into images that showed us the dark galaxy in radio frequencies. And perhaps over time, we would come to think of these radio maps as the true image of the galaxy. We might forget that the Milky Way was ever a visual object, ever something you could see with your eyes. The radio universe would become our reality, and visible light would become a historical curiosity, something our ancestors once used, but which we had evolved beyond. But some things would become much harder, even with new tools. Without visible stars, measuring distances across the galaxy would become far more challenging because astronomers often rely on stellar brightness and movement for calculations. Distance is one of the fundamental measurements in astronomy. Knowing how far away something is tells you how big it is, how bright it truly is, how fast it's moving. Distance is the key that unlocks almost every other piece of information about a cosmic object. But measuring distance is surprisingly difficult. Stars don't come with cosmic measuring tapes stretched between them. Instead, astronomers use clever techniques developed over centuries of observation. One method involves comparing how bright a star appears with how bright it actually is. If you know a star's true brightness, and there are certain types of stars whose brightness we understand quite well, then by measuring how bright it looks from Earth, you can calculate its distance. It's like seeing a light bulb in the distance and knowing how bright the bulb is, you can estimate how far away it must be. Another method uses parallax, the way nearby stars seem to shift position against more distant stars as Earth orbits the Sun. It's the same effect you see when you hold your thumb up and look at it first with one eye, then the other. Your thumb seems to move against the background. By measuring how much a star shifts, astronomers can calculate its distance through simple geometry. In a dark galaxy, both of these methods would fail. You can't measure apparent brightness if there's no light to measure. You can't detect parallax if you can't see the star's shifting position. Astronomers would have to rely on other techniques. Gravitational effects, perhaps. Watching how invisible objects orbit each other and using that motion to infer their masses and distances. Radio emissions, if the timing and strength of those emissions could be calibrated. Gravitational lensing, where the gravity of a massive object bends light, or in this case, other forms of radiation from objects behind it. But all of these methods would be harder, less precise, more dependent on assumptions and calculations. The cosmic distance ladder that astronomers have so carefully constructed would need to be rebuilt from scratch, using tools that were never designed for this purpose. The map of the galaxy would become uncertain, fuzzy, approximate, where once we knew distances to within a few percent, we might now be uncertain by factors of 2 or 3 or more. The precise universe would become a universe of estimates, and humanity would find itself in a strange new relationship with the cosmos. In the absence of natural cosmic light, humanity's view of the universe could become dependent almost entirely on machines capable of detecting invisible radiation. There's something profound about being able to look up at the night sky with your own eyes and see the universe. It's a direct connection. No instruments needed, no technology required. Just you and the cosmos, sharing a moment across the vast distances of space. That connection has shaped human culture for millennia. We've told stories about the stars. We've used them to navigate and measure time. We've found meaning in the patterns they form. The night sky has been a constant companion to humanity throughout our entire history. In a dark galaxy, that connection would be severed. The night sky would be blank, empty. There would be nothing to see with the naked eye, or at least almost nothing. Perhaps a few distant galaxies, faint smudges against the darkness. But nothing close, nothing familiar, nothing personal. Our understanding of the universe would become entirely mediated by instruments, by radio telescopes and infrared detectors and gravitational wave observatories, by computers that processed the data and converted it into forms humans could interpret, by screens that displayed false color images of a universe we could no longer directly perceive. This would change our relationship with the cosmos. It would become more abstract, more intellectual, less emotional. You can't form a personal connection with a radio map the way you can with the sight of the Milky Way stretching across the sky. You can't make wishes on graphs and data tables. Future generations might grow up never having seen the stars. They would learn about the universe through their instruments, through simulations and reconstructions. The cosmos would become something known rather than something felt. And perhaps something important would be lost in that transition. A sense of wonder, maybe, a feeling of being part of something vast and beautiful. The universe would still be there, still surrounding us, still full of marvels. But we would experience it secondhand, through the cold lens of technology. And that technology would have to guide us through space itself. Future space travelers might rely heavily on gravitational maps instead of visual star charts to navigate through the invisible galaxy. Navigation among the stars has always been about light. Sailors navigated by the position of stars above the horizon. Early spacecraft used star trackers, cameras that locked onto specific bright stars to determine their orientation. Even modern space probes use the positions of visible objects to figure out where they are and where they're going. In a dark galaxy, none of that would work. There would be no stars to track, no bright objects to use as reference points. Navigation would have to be reinvented from the ground up. Gravitational maps might become the solution. Every object with mass creates a gravitational field. Stars, planets, black holes, even in darkness, their gravity would remain, pulling on anything that passed nearby. By mapping these gravitational fields in detail, future navigators might be able to create charts showing where the invisible mass was concentrated in the galaxy. A spacecraft could then navigate by feeling its way through space. Sensors would detect the gravity of nearby objects. Computers would compare those readings with the gravitational maps, determining the ship's position the way you might determine your location in a dark room by feeling where the furniture is. It would be a strange kind of navigation. Instead of steering toward a bright destination, you'd be steering toward an invisible gravitational well. Instead of avoiding obstacles you could see ahead, you'd be avoiding mass concentrations your instruments detected. The journey would be guided by attraction and repulsion, by the push and pull of gravity, rather than by the light of distant suns. And it would be dangerous in new ways. Gravitational fields can change. A previously mapped region of space might contain new hazards, an invisible rogue planet that had drifted into your path, a stellar remnant your maps hadn't detected. You'd be traveling through the cosmos blind, trusting in maps that might be incomplete or outdated, hoping your instruments were sensitive enough to warn you before you encountered something catastrophic. And catastrophic encounters would still happen. The disappearance of starlight would make interstellar travel far more dangerous because spacecraft could no longer navigate using familiar constellations and bright stellar reference points. Imagine piloting a spacecraft through the galaxy. In our current universe, you would have constant reference points. You could look back and see the sun, yellow and familiar, receding behind you. You could look ahead and see your destination star growing brighter. Around you, the familiar patterns of nearby stars would shift slowly as you traveled, giving you a sense of motion, of progress, of where you were in three-dimensional space. Now imagine making the same journey in complete darkness. Your instruments tell you where you are, where you're going, how fast you're moving. But when you look out the window, you see nothing. Complete, unbroken blackness in every direction. You're traveling at thousands or millions of miles per hour through space that might contain hazards. Asteroids, comets, rogue planets, invisible stellar remnants. Your radar and other detection systems are watching for obstacles, but they have limited range. Something could be hurtling toward you from outside that range, and you wouldn't know until it was too late. And if something went wrong with your navigation systems, if your computers failed or your instruments gave you bad data, you would have no way to verify your position by independent observation. You couldn't look out and check your location against known stars. You couldn't use parallax or apparent motion to confirm you were on the right course. You would be completely dependent on your technology with no backup, no fail-safe, no way to cross-check your data against reality. It would be like flying an airplane through thick clouds, unable to see the ground. Except worse, because at least a pilot in clouds knows there will be ground somewhere below. In a dark galaxy, you might not know if you were still on course or had drifted off into empty space until you'd been lost for months or years. Interstellar travel would become an act of tremendous faith. Faith in your instruments, faith in your maps, faith that the universe you couldn't see was still where your calculations said it should be. And even from a distance, dangers would be harder to detect. In a completely dark galaxy, collisions between invisible stars and objects would still happen, but detecting them would become far more difficult for scientists. Right now, when stars collide, when two stellar remnants spiral into each other, or when a wandering star passes through a dense cluster, we can see it happen. We detect the burst of light, the nova or supernova that results. We watch the shock waves expanding through space. We study the aftermath in multiple wavelengths of light. These collisions are rare, but they're important. They tell us about stellar dynamics, about the density of different regions in the galaxy, about how matter behaves under extreme conditions. They're laboratories for physics, natural experiments that produce conditions we could never recreate on Earth. In a dark galaxy, many of these collisions would become invisible. If two dead stars, white dwarfs or neutron stars or black holes, collided, there might be no visible light produced at all. The event would happen in darkness, detectable only if we were lucky enough to have the right instruments pointed in the right direction at the right time. Some collisions might still produce gravitational waves, ripples in space-time itself traveling outward at the speed of light. We've built observatories to detect these waves, and they work regardless of whether the colliding objects produce light. But gravitational wave detectors can only sense the most powerful collisions, and only if they're relatively nearby. Smaller collisions, or those farther away, would go unnoticed. The galaxy would become a place where violence occurred in silence, where catastrophic events unfolded unseen, where the universe continued its endless cycle of destruction and creation, but did so in shadow, witnessed by no one. Scientists studying the evolution of the galaxy would lose crucial data. They would have to rely on statistics and modeling, on theoretical calculations of how often collisions should happen, rather than on direct observations of collisions actually happening. Their understanding would become more approximate, more uncertain. The universe would keep its secrets more closely in the darkness. And not just collisions would become harder to detect. If advanced alien civilizations existed elsewhere in the Milky Way, humanity could lose one of its best ways of detecting them, since many searches rely on observing starlight changes. For decades, We've been searching for signs of intelligent life in the galaxy. One method involves looking for unusual patterns in radio signals. The famous SETI project, listening for messages from the stars. Another method, developed more recently, involves looking for changes in starlight that might indicate alien megastructures. The most famous example is the search for Dyson spheres, hypothetical structures that an advanced civilization might build around their star to capture all of its energy output. Such a structure would block the star's light in characteristic ways, creating a signature that telescopes might detect. We've also looked for dimming patterns that might indicate large orbital structures, planet-sized solar panels, or other evidence of engineering on a massive scale. Any civilization advanced enough to be modifying their solar system would likely leave signs visible in how their star's light reaches us. In a dark galaxy, this entire approach would fail. There would be no starlight to block, no patterns to detect. An alien civilization could build anything they wanted around their dead star, and we would never see it. They could have a thriving interstellar empire with colonies and megastructures and all the signs of advanced intelligence. But if those signs were optical, we'd be blind to them. Perhaps we could still detect them through radio signals if they were broadcasting, through infrared signatures if their structures retained any heat, through gravitational effects if their constructions were massive enough. But many of our best detection methods would simply stop working. The galaxy could be full of intelligence, full of civilizations as curious about the universe as we are, and we would have no way to find them. We would drift through a dark galaxy, alone as far as we could tell, never knowing that we were surrounded by others facing the same darkness. It would be cosmic loneliness on a profound scale, not the loneliness of being the only intelligence in the galaxy, but the loneliness of being unable to detect the others you shared it with. Yet darkness would reveal some things more clearly. The bright glow from distant quasars outside the Milky Way could become easier to notice once our own galaxy stopped flooding the sky with light. Quasars are among the most luminous objects in the universe. They're powered by supermassive black holes at the centers of distant galaxies, consuming matter at tremendous rates. As that matter spirals inward, it heats up and emits enormous amounts of radiation. So much that a single quasar can outshine an entire galaxy of hundreds of billions of stars. Most quasars are billions of light years away, in galaxies far beyond the Milky Way. Right now, we can detect them, but they're faint from our perspective. Distant points of light that require powerful telescopes to study in detail. But in a dark Milky Way, with no local stars flooding the sky with light, quasars might become more prominent. The sky would be darker, and against that darkness, these distant beacons would stand out more clearly. They would be like lighthouses seen across an ocean of night, the only points of light in an otherwise empty sky. Astronomers in a dark galaxy might focus their attention on these distant objects. They would study quasars and distant galaxies, trying to understand the universe beyond their own invisible neighborhood. They might come to know more about the distant cosmos than about their own galaxy, simply because the distant cosmos was still visible. It would be a strange inversion, the far becoming more familiar than the near, the distant becoming more real than the local. The universe billions of light years away being better understood than the space just thousands of light years from home. And there would be one other source of light, ancient, faint, but still present, the cosmic microwave background, faint leftover radiation from the early universe, might become one of the few detectable sources of light-like energy remaining in the sky. Shortly after the Big Bang, about 380,000 years after the beginning of time, the universe cooled enough for atoms to form. At that moment, light that had been scattered by free electrons suddenly became able to travel freely through space. That light has been traveling ever since, stretched by the expansion of the universe into microwave wavelengths. We call it the cosmic microwave background, or CMB. It's everywhere, coming from every direction. A faint glow that represents the oldest light in the universe. It's incredibly faint. Your eyes can't see it, and it requires sensitive instruments to detect. But it's always there, a whisper from the beginning of time. In a dark Milky Way, the CMB might become one of the few electromagnetic signals still detectable in the sky. With no stars, no nebulae, no local sources of light, astronomers might find themselves studying this ancient radiation more than anything else. And perhaps there would be something poetic about that. In the darkest moment of the galaxy's history, when all the stars had gone out and the cosmos seemed cold and empty, there would still be this faint reminder of the very beginning. The light from the birth of the universe would still be reaching us, still carrying information about conditions in the earliest moments of time. It would be a connection across vast ages, a thread linking the dark present to the brilliant past, evidence that even in the deepest darkness, even when everything seemed to have ended, the universe remembered its beginning. And in that memory, perhaps there would be hope. Science would continue even in the dark age. It would evolve, adapt, find new ways to ask questions and seek answers. The tools would change, the methods would transform, but the fundamental curiosity that drives us to understand the cosmos would remain. Even in darkness, we would still search for truth. Close your eyes and imagine. Not just a moment of darkness, but entire futures unfolding in it. Civilizations adapting. Life persists in ways we never anticipated. The galaxy continues its ancient rhythms even as everything visible about it has changed. This is where we turn now to the question of what comes next. What persists? What endures when the light is gone? If alien life existed on planets orbiting red dwarf stars, those worlds might cool more slowly because red dwarfs can release heat steadily for extremely long periods. Red dwarf stars are the universe's marathon runners. They're small, barely massive enough to sustain fusion in their cores, but that modest size gives them an extraordinary advantage. They burn their fuel slowly, so slowly that even the oldest red dwarfs in the universe, formed billions of years ago, are still shining today. And they'll continue shining for trillions of years into the future, far longer than the universe has existed so far. In our scenario where the Milky Way goes dark, we've imagined all stars losing their light. But let's consider for a moment what would happen if the darkness came more gradually, or if red dwarfs retained some residual heat even after fusion stopped. These small stars would cool more slowly than their larger cousins. The planets orbiting them might remain warm, not hot, perhaps, but above freezing, for thousands or even millions of years after the light went out. Any life that had evolved on worlds circling red dwarfs might have more time to adapt, more time to find solutions. Where life around sun-like stars might face immediate catastrophe, life around red dwarfs might have generations to prepare, to adjust, to find ways to survive in the cooling darkness. Underground ecosystems might develop, drawing on whatever geothermal heat remained in the planet's core. Biological processes might slow down, organisms entering something like suspended animation, waiting for conditions that might never improve but not quite succumbing to extinction either. Life hanging on by a thread, but hanging on nonetheless. These worlds would be havens in the darkness. Small pockets of relative warmth in a freezing galaxy. Islands of possibility in an ocean of cold. And if intelligence existed on any of these worlds, they might look out at the dark sky and wonder if they were the last ones left. The final ember of consciousness in a universe that had gone cold. Some icy moons in the galaxy, such as Europa or Enceladus, could remain warmer than expected because of internal heating beneath their frozen surfaces rather than sunlight alone. Right here in our own solar system, there are worlds that don't depend on sunlight for their warmth. Jupiter's moon Europa, for instance. Its surface is covered in thick ice, frozen solid at temperatures far below zero. But beneath that ice, scientists believe there's a vast ocean of liquid water, an ocean that might be larger than all of Earth's oceans combined. How is this possible so far from the Sun? The answer is tidal heating. Europa orbits Jupiter in an elliptical path, and as it does, Jupiter's enormous gravity flexes and squeezes the Moon. This constant kneading generates heat through friction, the same way bending a paper clip back and forth makes it warm. That heat is enough to keep water liquid beneath the ice. Saturn's moon Enceladus shows similar signs. It has geysers that shoot water vapor and ice particles into space from cracks in its frozen surface. That water is coming from somewhere liquid, somewhere warm, despite being nearly 1 billion miles from the Sun. In a dark Milky Way, after the Sun had gone cold, these moons might actually fare better than Earth. Earth depends on solar radiation for almost all of its heat. But Europa and Enceladus would still have their tidal heating and still have their internal warmth. The ice on their surfaces might thicken, forming barriers miles deep, but underneath, those oceans might persist. And if life exists in those oceans now, as some scientists suspect it might, it could continue existing in the darkness. Simple organisms, perhaps, feeding on chemical energy from hydrothermal vents on the ocean floor, never knowing that the galaxy above them had gone dark, never realizing that they had become some of the last living things in their corner of space. These icy moons would become sanctuaries, places where the basic conditions for life persisted not because of stellar light, but because of the orbital mechanics and gravitational relationships between worlds. Life continues not through the generosity of a star, but through the subtle physics of bodies in motion. If all stellar fusion stopped, the creation of new heavier elements inside stars would also end, changing the long-term chemical evolution of the galaxy. We are made of star stuff. It's one of the most poetic truths in science, and it's literally accurate. Every atom in your body heavier than hydrogen was forged in the core of a star or in the violence of a supernova. The carbon in your cells, the oxygen you breathe, the calcium in your bones, the iron in your blood, all of it was created by fusion reactions in stars that lived and died before our solar system even formed. This process is ongoing. Right now, throughout the galaxy, stars are fusing lighter elements into heavier ones. Hydrogen becomes helium. Helium becomes carbon and oxygen. In the most massive stars, the process continues up the periodic table, creating silicon, sulfur, iron. And when those massive stars die, they explode, scattering these heavier elements into space where they can be incorporated into new stars, new planets, new forms of matter. In a dark galaxy where fusion had stopped, this cosmic alchemy would end. No new heavy elements would be created. The universe would be left with whatever chemical composition it had at the moment the darkness began. And from that point forward, that composition could only become simpler, never more complex. Over vast timescales, this would matter. Radioactive elements would decay into lighter, stable forms. Complex molecules would break down under cosmic radiation. Slowly, inexorably, the chemical richness of the universe would diminish. Any civilizations trying to survive in the darkness would find themselves with a fixed inventory of elements. They couldn't mine stars for fresh materials because stars would no longer be producing them. They would have to carefully manage whatever resources existed, knowing that certain elements, once used, could never be replaced. It would be a universe running down. Not all at once, not in any human timescale, but over billions of years, becoming simpler, less interesting, less capable of supporting the complex chemistry that makes life possible. The darkness wouldn't just be the absence of light. It would be the end of creation itself. Temperatures in Earth's upper atmosphere would rapidly change after solar radiation disappeared, causing major shifts in the behavior of the atmosphere itself. We think of Earth's atmosphere as a single thing, but it's actually made up of distinct layers, each with its own characteristics. The lowest layer, the troposphere, is where we live, where weather happens. Above that is the stratosphere, then the mesosphere, then the thermosphere reaching up hundreds of miles above the surface. The upper layers of the atmosphere are heated directly by solar radiation. High-energy ultraviolet light from the sun strikes atoms and molecules in these regions, exciting them, heating them to temperatures that can reach thousands of degrees. This heating creates structure in the atmosphere, causes winds and circulation patterns, and affects how radio waves propagate. When the sun went dark, this heating would stop immediately. Well, not quite immediately. It would take about 8 minutes for the last sunlight to reach Earth, traveling at the speed of light. But after that, the upper atmosphere would begin cooling rapidly. The thermosphere, which can reach temperatures of 2,500 degrees Celsius when heated by the sun, would start to cool and contract. The boundary between space and atmosphere would shift. Satellites in low orbit might experience slightly less drag. Radio communications would be affected as the ionosphere, a region of charged particles in the upper atmosphere, began to dissipate. Lower down, changes would come more slowly. The troposphere, where we live, is insulated by the layers above it and warmed partly by heat radiating from Earth's surface. But even here, within days, temperatures would begin to plummet. The atmosphere would start to behave in strange ways. Without solar heating to drive weather systems, global wind patterns would break down. Storms would lose their energy source. The jet streams that guide weather across the planet would weaken and eventually stop. And as the surface cooled, the atmosphere would begin to condense. Water vapor would freeze and fall as snow. Eventually, even the gases that make up air would begin to liquefy. Oxygen and nitrogen, normally gaseous at Earth's temperatures, would form puddles and then lakes and then oceans of liquid air on the frozen surface. The atmosphere wouldn't disappear entirely, but it would change state, collapsing down to the surface, leaving the upper regions of what we once called sky nearly empty. Earth would become a world with almost no atmosphere, just a thin shell of frozen gases clinging to a dark, ice-covered surface. Without the sun's radiation pushing against them, some particles and gases in the solar system would begin behaving differently over long periods of time. The sun doesn't just provide light and heat, it also creates a constant wind. The solar wind, a stream of charged particles that flows outward from the sun in all directions at nearly 1,000,000 miles per hour. This wind shapes the space around us in ways we don't always appreciate. It pushes on comets, creating those beautiful tails that always point away from the sun. It creates a bubble around the solar system called the heliosphere, a region where the solar wind dominates over the interstellar medium. It affects how cosmic rays, high-energy particles from distant supernovae and other violent events can penetrate into the inner solar system. When the sun went dark, the solar wind would stop. The heliosphere would collapse. Suddenly, interstellar space would flood inward, bringing with it particles and radiation that had been held at bay. Dust in the solar system would start to behave differently. Without radiation pressure from the sun pushing small particles outward, they would gradually spiral inward under the weak pull of gravity. Over millions of years, this dust might accumulate, forming new structures or falling into the planets and asteroids. Comets would lose their tails. Those spectacular displays of gas and dust streaming away from icy bodies would cease. The comets would become just dark rocks drifting through darkness, indistinguishable from asteroids except for their composition. The entire character of the solar system would shift. It would become less dynamic, less influenced by the constant pressure and energy from the sun. It would become more like interstellar space, cold, dark, filled with particles drifting under gravity alone. The solar system would become just another patch of the galaxy, no longer distinguished by having an active star at its center. Just one more collection of dead worlds orbiting an invisible point in space. The darkness could make meteors appear more dramatic for a short time, as fiery rocks burned brightly against an otherwise pitch-black sky. Here's a strange thought. In the brief period after the stars went out but before everything froze completely, before atmospheres condensed and life ended, there would be a window where some things became more visible, not less. Meteors, for instance. Right now, when a piece of space rock enters Earth's atmosphere at tremendous speed, friction with air molecules heats it until it glows, creating a streak of light across the sky. We call these shooting stars, though they're not stars at all, just tiny pieces of cosmic debris burning up as they fall. On a normal night, these meteors are pretty, but not spectacular. They're bright streaks against a dark sky, but a sky that still contains stars, moonlight, and light pollution from cities. There's a lot of visual competition. In a dark world with no sun, no moon, no stars, no city lights, a meteor would be the only light in the entire sky. It would streak across pure blackness, a sudden brilliant flash in total darkness. For those few seconds as it burned, it would be the brightest thing in existence, drawing every eye that could still see. It would be beautiful in a haunting way, a reminder that motion and energy still existed in the universe, that not everything had become static and cold. Each meteor would be like a small rebellion against the darkness, a brief return of light before it extinguished itself. And then it would be gone, and the darkness would close in again, complete and total. In those final days, people might gather to watch for meteors, hoping to see one more flash of light, one more moment of brightness before the end. Space probes traveling beyond the solar system would continue moving through the invisible Milky Way, carrying records of humanity into a dark cosmic ocean. Right now, several spacecraft from Earth are on their way out of the solar system. Voyager 1 and Voyager 2, launched in the 1970s, have already crossed the boundary into interstellar space. They're still functioning, still sending back data, though they're so far away now that their signals take hours to reach us. These probes carry golden records, actual phonograph records with sounds and images from Earth, intended as messages to any alien intelligence that might someday find them. Music, greetings in multiple languages, images of humans and our world. Time capsules sent into the void. In a dark Milky Way, these probes would continue their journeys. They don't need light to function. Their power comes from radioactive decay, not solar panels. They would drift through the darkness, moving at tens of thousands of miles per hour relative to the sun, crossing light years over millions of years. They would pass invisible stars, dark planets, objects no one could see but which still exerted their gravitational pull. The probes would be affected by these encounters, their trajectories bent slightly by each massive object they passed, their paths becoming increasingly complex and unpredictable over time. And they would carry their records, physical artifacts from a civilization that once existed, from a time when stars still shone. If any intelligence ever found them, those records would be evidence of what had been lost. Proof that there was once light in the universe, that life had evolved under that light, that consciousness had emerged and looked up at the stars and wondered what was out there. The probes would be messages in bottles, floating on a dark ocean, most likely never to be found, never to be read, but traveling nonetheless, carrying their precious cargo forward through the ages, through the endless night. They would be humanity's legacy in a dark galaxy. Our last words were sent out into a universe that could no longer hear them. Civilizations living on distant planets might never realize they were inside a spiral galaxy if their stars had always been dark, leaving them trapped in cosmic ignorance. Imagine being born into a civilization on a planet circling a dead star in a dark galaxy. You've never seen a star. Your ancestors never saw stars. No one in your entire history has ever looked up and seen light in the sky, except perhaps from distant quasars billions of light years away. You would know, from your instruments, that your world orbited something massive. You could detect its gravity, map its presence. You would call it your sun, even though it produced no light. You might even understand, theoretically, what fusion is, what light is, even though you'd never experienced these things directly. But would you ever figure out that you were inside a galaxy? That you were surrounded by hundreds of billions of other stars, all equally dark, arranged in a vast spiral structure? How could you possibly discover that? Optical astronomy would be useless. Radio astronomy might map out some nearby objects, but the galaxy is so large that understanding its overall structure from within it is incredibly difficult even when you can see stars. Without that visual information, without being able to look up and see the Milky Way stretching across the sky, how would you know? You might measure gravitational gradients, notice that there was more mass in one direction than another. You might detect the rotation of your solar system around some distant point. With enough time and enough sophisticated instruments, you might piece together the truth. But it would be hard. So hard that your civilization might never accomplish it. You might live and die and pass through your entire history thinking you existed in a mostly empty universe, with just your solar system and perhaps a few nearby objects you detected. You would never know you were part of something vast and structured and beautiful. It would be a tragedy of cosmic proportions. Living inside a galaxy and never knowing it. Being surrounded by billions of worlds and thinking you were alone. The truth would be hidden behind darkness so complete that not even millions of years of science could pierce it. If humanity survived long enough, people might genetically adapt to darker environments, relying more on technology or enhanced low-light vision. Evolution doesn't stop. It can't stop. As long as there's life and reproduction and variation, natural selection will continue to shape organisms to better fit their environments. And if humanity somehow survived into a dark future, we would adapt, change, become something different. Our eyes would be among the first things to change. Right now, human vision is optimized for daylight conditions. We have color vision, we can see fine details, but we're not particularly good at seeing in low light compared to many animals. In a darker world, those priorities would shift. Over thousands of generations, natural selection might favor individuals with larger pupils, more rod cells in their retinas, better signal processing in the parts of the brain that handle vision. We might lose color vision entirely. It's metabolically expensive and useless in darkness. We might develop tapetum lucidum, the reflective layer behind the retina that makes cats' eyes glow and helps them see in near darkness. But genetic adaptation would only go so far. You can't evolve to see without any light at all. Physics won't allow it. So we would also adapt technologically. Perhaps we would augment ourselves with artificial sensors that could detect infrared radiation, radio waves, gravitational fields. We might develop implants that translated these invisible signals into something our brains could interpret as vision, creating a sensory experience of the universe even though our eyes received no light. We might become less dependent on vision altogether, enhancing our other senses or developing entirely new ones. Human culture and psychology might shift to value hearing or touch more than sight. And over very long timescales, we might become something that wouldn't quite be human anymore. Still intelligent, still conscious, still carrying the legacy of our origins, but adapted to a dark universe in ways that would make us unrecognizable to our ancestors. We would become children of the darkness, born into it, shaped by it, unable to imagine what it must have been like to live in a universe full of light. A completely dark Milky Way would still move through space alongside other galaxies, continuing its slow future collision course with the Andromeda Galaxy. The Milky Way and the Andromeda Galaxy are on a collision course. Not a collision in the sense of crashing and exploding. Galaxies are mostly empty space, so when they merge, most of their stars will simply pass through the spaces between each other. But the gravitational interaction will be dramatic, pulling both galaxies out of shape, triggering waves of star formation. Normally, this collision is scheduled to begin in about 4 billion years. Right now, Andromeda is moving toward us at about 250,000 miles per hour. It seems slow on cosmic scales, but over billions of years, that adds up. In a dark Milky Way, this collision would still happen. Darkness wouldn't change the gravity. The two galaxies would still be pulling on each other, still moving closer together with each passing million years. But the collision would be invisible. Two dark galaxies drifting together through space, their invisible stars beginning to interact, their gravitational fields beginning to merge. From the outside, if anyone were watching, they would see nothing, just empty space where two galaxies used to be. The merger would take billions of years. The two galaxies would pass through each other, their shapes distorted by tidal forces, then swing back around for another pass. Eventually, they would settle into a new configuration. A single larger galaxy, elliptical rather than spiral, containing all the stars of both the Milky Way and Andromeda. All of this would happen in darkness. A cosmic dance performed on a stage with no lights. The grandest show in the local universe, and no one able to see it. The new galaxy, formed from the merger, would drift through space for billions more years. Still full of mass, still containing hundreds of billions of invisible stars, still orbiting its own center, still held together by gravity. And perhaps in that distant future, something would change. Perhaps the conditions would arise for new stars to form. Perhaps some catalyst, some compression of gas during the merger, would trigger the collapse of those ancient molecular clouds that had been waiting for so long. And perhaps, just perhaps, light would return. Not everywhere at once, but in pockets. New stars igniting in the darkness. Small at first, just a few, then spreading as their radiation triggered more star formation. A renaissance of light in a galaxy that had been dark for billions of years. Or perhaps not. Perhaps the darkness would continue forever. Perhaps the merged galaxy would drift through space eternally, a ghost among the visible galaxies, forever carrying within it the memory of what it once was, but never able to return to that bright state. Either way, it would continue, moving, existing, persisting through the darkness and into whatever future the universe held. Because that's what the cosmos does. It endures, continues. Light or dark, it carries on. There is something profound about memory, about the way we hold onto things that are gone, about how the past shapes us even when it exists only in our minds, in our stories, in the artifacts we leave behind. And now we arrive at the final question. Not what would happen if the Milky Way went dark, but what would be remembered, what would be lost, what traces would remain of the light that once was. Astronomers estimate the Milky Way contains over 100 billion stars. If all of them went dark, one of the largest visible structures in the universe would effectively disappear. 100 billion. It's a number so large that it's almost meaningless to the human mind. We can write it, we can say it, but we can't really comprehend it. If you tried to count to 100 billion, counting one number per second without stopping, it would take you more than 3,000 years. Each one of those numbers would represent a star. A sun like ours, or larger or smaller, but a massive ball of fusing hydrogen nonetheless. And around many of those stars, there would be planets, moons, asteroid belts, entire solar systems, each one a complex gravitational dance of objects large and small. All of that would still exist in a dark galaxy. Every single star, every planet, every moon. The matter wouldn't disappear. The structure wouldn't collapse. But it would become invisible, undetectable to ordinary observation, hidden behind a veil of darkness so complete that the entire galaxy would vanish from sight. From another galaxy, looking toward our region of space, observers would see nothing where the Milky Way used to shine, a gap in the cosmic landscape, an absence where there should be presence. They might wonder if their records were wrong, if ancient star maps showing a galaxy in that location were somehow mistaken. But the galaxy would still be there, silent, dark, waiting, 100 billion stars, and all of them invisible. It would be like a city where every light had been turned off at once, where millions of buildings still stood but could no longer be seen. The universe would lose one of its grandest sights, and those who remembered what it looked like would carry that loss with them forever. Future generations born after the darkness might struggle to understand what stars once looked like, learning about them only through ancient recordings and stories. Imagine trying to explain the sun to someone who had never seen it, never felt its warmth on their skin, never watched it rise in the morning or set in the evening, never experienced the way light fills the world and makes everything visible. You might show them pictures, videos. You might describe the color, the brightness, the way it hurt to look directly at it. You might explain how it moved across the sky, how it created shadows, how it made the blue of the sky and the gold of sunset. But would they truly understand? Could they really grasp what you were describing, or would it remain abstract to them? A concept they knew intellectually but couldn't feel, couldn't internalize, couldn't make real in their minds. This would be the challenge facing future generations in a dark galaxy. They would have records from before the darkness, photographs of starry skies, time-lapse videos of the Milky Way wheeling overhead, measurements and data and descriptions, an entire archive of what had been lost. And they would study these records, learn from them, memorize the names of constellations they could never see, calculate the distances to stars that were invisible, understand, in theory, what their ancestors had witnessed every night. But it wouldn't be the same. Couldn't be. You can't truly know light by studying pictures of it in darkness. You can't feel the warmth of the sun by reading about temperature measurements. Some things have to be experienced to be understood. And so, despite all the knowledge preserved, despite all the efforts to teach and explain and keep the memory alive, something essential would be lost. A gap would exist between those who had seen the stars and those who only knew of them. A gap that no amount of education could fully bridge. The memory would persist, but it would grow pale, abstract, distant, like trying to remember a dream upon waking, knowing it was vivid and real when you were in it, but unable to recapture that feeling once you've returned to the waking world. Future children born under the darkened sky might think stars were fictional objects invented in old stories rather than real suns that once filled the heavens. Children believe what they experience. If you grow up in a world where the sky is always dark, where there are no stars, no moon, no sun except in ancient stories and pictures, what would you believe? You might think stars were like dragons, mythical objects that people made up, things that sounded wonderful and magical but couldn't possibly be real. Your teachers would insist they were real, would show you the evidence, the old photographs and videos. But photographs can be faked. Videos can be manipulated, especially as they get older, as generations pass and the technology that created them becomes ancient and incomprehensible. And the stories about stars would sound like fairy tales. Enormous balls of fire floating in the sky, so bright you couldn't look at them directly, so hot they warmed entire planets from millions of miles away. Billions of them scattered through space, some grouped into patterns that people named and told stories about. It would sound impossible, too fantastical to be true, like someone claiming that mountains could fly or oceans could float in the air. The physics would make sense when your teachers explained it, but the reality would feel unreal. Some children would believe anyway, trusting the education they received. Others would be skeptical, thinking their elders were passing down myths and calling them history. And as generations passed, as the living memory of the stars faded and all that remained were records and stories, that skepticism might grow. Debates would arise, scholars arguing about whether the photographs were genuine or elaborate hoaxes. Philosophers questioned whether light itself, as described in the old texts, was physically possible. Revisionist historians suggest that the Age of Stars was a cultural myth, a golden age story that every civilization tells itself about the past. And through it all, above their heads, 100 billion stars would still exist. Dark, silent, invisible, the truth hanging in the sky, undetectable, while people argued about whether it had ever been real. Ancient monuments aligned with stars, such as pyramids and observatories, would lose their celestial reference points in the darkened sky. Humans have been building monuments to the stars for thousands of years. The Great Pyramid of Giza has shafts aligned with specific stars. Stonehenge marks the solstices and equinoxes. The ancient Maya built observatories to track Venus and predict eclipses. Cultures around the world created stone circles, temples, and structures that oriented themselves to celestial events. These monuments are more than just buildings. They're connections between earth and sky. They're statements in stone saying that what happens up there matters, that the movements of the cosmos are worth tracking, worth honoring, worth building permanent structures to observe and remember. In a dark galaxy, all of these alignments would become meaningless. The pyramids would still point toward where certain stars used to be, but nothing would be there to see. Stonehenge would still mark the sunrise at the solstice, but there would be no sun to rise. The Maya observatory would still have its viewing angles, but Venus would be dark and invisible. Future archaeologists studying these monuments would puzzle over their purpose. They would find records explaining the astronomical alignments, describing which stars or planets were supposed to appear at which windows or along which sightlines. But they wouldn't be able to verify any of it. The sky would be blank. Some might conclude the alignments were coincidental, that ancient people happened to build in certain directions and later cultures invented astronomical explanations. Others might trust the records and understand that these monuments were frozen in time, pointing forever at celestial markers that no longer revealed themselves. The monuments would become tombstones for the stars, permanent reminders of what had been lost, places where people could stand and look up at darkness and try to imagine what their ancestors had seen. Try to picture light streaming down from the places these ancient stones pointed to. They would be memorials to memory itself, to the act of remembering, to the human impulse to mark and measure and honor the cosmos, even when the cosmos no longer showed itself. Future archaeologists on surviving worlds might discover ancient records showing that the galaxy was once filled with light, turning the bright Milky Way into a forgotten cosmic memory. Archaeologists dig through layers of time. They find artifacts, texts, buildings. They piece together the past from fragments, from clues left behind by people who never imagined anyone would be searching for them. In a dark future, archaeologists might excavate the ruins of observatories, find old telescopes corroded and broken, designed to collect light that no longer came, discover data storage devices, if they could still be read, containing images of nebulae and star clusters and galaxies. Unearth journals written by astronomers describing what they observed on specific nights, listing coordinates of stars and calculating their distances. And from all of this evidence, they would reconstruct a strange truth, that there was once light in the universe, that the sky was not always empty, that their ancestors lived under a canopy of stars and took it for granted, the way people take air for granted, never imagining it might someday be gone. It would be like discovering that Earth once had a different sky. a revelation that would change everything they thought they knew about the past. The galaxy wouldn't just be dark in their present. It would be a place that had lost something, a diminished version of what it once was. Some of these archaeologists might feel grief for what they'd never experienced, a sense of loss for something that ended before they were born. They would look at images of the Milky Way stretching across Earth's night sky and feel a longing for something they couldn't have. A world of light and warmth and visible stars that existed only in the past. Others might feel wonder, amazement that the universe could change so dramatically, that what seemed permanent and eternal could fade and vanish. It would challenge their assumptions about the nature of reality, about what could be counted on to endure. And the bright Milky Way would pass from history into memory, and from memory into legend. Each generation further removed from the light, each one understanding it a little less clearly, until it became as distant and unreal as the Big Bang itself. A cosmic event that happened long ago, important but incomprehensible, known but not felt. Over millions of years, the memory of a bright galaxy could slowly turn into myth, with future civilizations debating whether stars ever truly existed at all. Myths are stories that contain truth but are no longer quite believed. They're the tales that cultures pass down, generation after generation, that might be based on real events but have been transformed through retelling into something more symbolic than factual. Give it enough time, give it millions of years, and the memory of a bright galaxy could undergo this transformation. The historical fact of stars would become the mythological story of stars. A tale from the distant past that might be true, might be metaphorical, might be completely invented. Future civilizations would have ancient texts describing stars. Religious scriptures might speak of celestial lights as the domain of gods. Scientific treatises from millions of years ago might explain fusion and stellar evolution. Philosophical works might meditate on the meaning of a universe filled with light. But these texts would be old, unimaginably old, written in languages that had to be deciphered, using concepts that had to be reconstructed, referring to technologies and observations that couldn't be replicated. How much trust could you place in them? How literally could you interpret them? Debates would rage in universities and temples. Literalists would insist that stars were real, exactly as described in the ancient texts. Allegorists would argue that stars were metaphors for something else, perhaps for knowledge or enlightenment or divine presence. Skeptics would claim the entire concept was invented, a useful fiction that ancient people created to explain natural phenomena they didn't understand. Evidence would be brought forward on all sides, artifacts that seemed to support the existence of stars, alternative interpretations that explained the same artifacts without requiring belief in impossible lights in the sky, textual analysis showing how stories about stars evolved over time, suggesting they were cultural constructs rather than historical facts. And the truth would be there all around them, impossible to detect but undeniably real. 100 billion stars still existing in the darkness, still orbiting the galactic center, still holding planets in their gravitational embrace. The universe would know they were real, but the civilizations living within it might not. Belief in stars might become a matter of faith rather than knowledge, something you either accepted or rejected based on your interpretation of ancient wisdom. The line between history and mythology would blur until it vanished entirely. And perhaps that would be the cruelest aspect of the darkness. Not just that it took the stars away, but that it took even the memory of them. That it made reality itself questionable. That it turned truth into myth and left future generations arguing about whether the cosmos had ever been different from the dark void they experienced. Astronauts on the International Space Station would witness Earth turning into a dim, frozen sphere surrounded by endless blackness. In those final hours, as the sun dimmed and went out, there would be people in space. Astronauts orbiting Earth, living and working aboard the International Space Station or whatever vessels existed in that future. They would have a unique perspective. They would watch it happen from above. See the last light fading across Earth's surface. Watch as the Terminator, the line between day and night, makes its final passage around the planet. See the lights of cities below, glowing briefly brighter in the darkness before they too began to fail as power systems collapsed. They would see Earth change. The blue and white and green and brown of our living world, so beautiful from orbit, so vibrant and full of color, would begin to fade. Clouds would freeze and fall as snow. Oceans would start to ice over, the freezing spreading from the poles toward the equator. The green of forests would vanish as vegetation died. Within days, perhaps weeks, Earth would be transformed. A sphere of ice reflecting no light because there was no light to reflect. The atmosphere beginning to condense and fall as temperatures dropped below the point where gases could remain gaseous. And around this dying world, the astronauts would see nothing. No stars, no Sunday, no moon, just blackness in every direction. Endless, complete, overwhelming blackness. They would be floating in a void, watching the only light in existence slowly extinguish below them. Some would try to return to Earth, knowing it was futile, knowing there was no salvation on the surface but feeling the pull of home anyway. Others would stay in orbit as long as their life support held out, witnessing the end, bearing witness to the transformation of everything they'd ever known. And when their power failed, when their heat ran out, when their air became unbreathable, they would drift. Dead vessels in orbit around a dead world, circling in the darkness for millennia, monuments to the last moments of light. Future space explorers might drift through the invisible Milky Way feeling completely alone inside an endless cosmic void. Imagine being an explorer in that dark future. Your vessel moving through space, traveling between invisible stars, navigating by instruments alone. Outside your window, nothing, just perfect, absolute blackness in every direction. You would know intellectually that you weren't alone. Your instruments would detect mass nearby, gravitational fields indicating stars and planets, radio signals perhaps from other civilizations, if any had survived. You would have maps showing where things should be, calculations predicting what you would encounter. But you wouldn't see any of it. You could travel right past a star, close enough that it would fill the sky if it were visible, and you would see nothing. Your ship could be surrounded by planets, moons, asteroids, and your eyes would report only emptiness. The psychological impact would be profound. Humans are social creatures. We take comfort in the presence of others, in knowing we're not alone. Even seeing distant stars gives us that comfort. There are other suns impossibly far away, but they're there. They prove the universe is populated, that there are other places, other things, other possibilities. In total darkness, that comfort would be gone. You would feel alone in a way that few humans have ever experienced. Alone not just from other people, but from everything. Floating in a void that seemed empty even though you knew it wasn't. Surrounded by invisible walls you couldn't see, couldn't touch, couldn't confirm except through instruments you had to trust absolutely. Some explorers might not be able to handle it. The isolation, the sensory deprivation, the cognitive dissonance of knowing you're surrounded by things you can't perceive. They might refuse to travel, might suffer psychological breaks, might insist on returning to whatever world they came from even if it meant abandoning their mission. Others would adapt, would learn to trust their instruments more than their eyes, would find ways to cope with the darkness, to make peace with the void. They would become a new kind of human, suited to a new kind of universe. Explorers of the invisible, travelers through darkness, but even they would feel it, the loneliness, the emptiness, the sense of drifting through eternity with nothing to mark their passage, Nothing to indicate they were moving at all except the changing numbers on their navigation displays. The galaxy's ancient star clusters would still drift through space invisibly, carrying some of the oldest objects in the universe hidden within the darkness. Scattered throughout the Milky Way are globular clusters, dense balls of hundreds of thousands of stars, all bound together by gravity, all orbiting the galactic center as a unit. These clusters are ancient. Some of them formed more than 12 billion years ago, when the universe itself was less than 2 billion years old. The stars in these clusters are old and cool, red giants and white dwarfs, objects at the end of their lives, slowly fading, releasing the last of their energy before going dark forever. In our current galaxy, you can see some of these clusters with the naked eye. Dim, fuzzy patches against the star fields. Through a telescope, they resolve into dense concentrations of stars, so tightly packed that near the center they must be separated by just light weeks or light days rather than light years. In a dark galaxy, these clusters would still exist, still drifting through space on their ancient orbits, still gravitationally bound, their stars still orbiting the cluster's center of mass, but completely invisible. Dark concentrations of dark stars, noticeable only through their collective gravity. These clusters would be archives, collections of the oldest matter in the galaxy, preserving conditions from the early universe. If you could study them, if you could detect and analyze the invisible stars within them, you would learn about cosmic history, about what the universe was like when it was young, about how the first generations of stars formed and evolved. But in darkness, that history would be locked away. The clusters would drift through the galaxy silently, carrying their ancient knowledge but unable to share it. Time capsules from the dawn of the cosmos, sealed by the absence of light. And within them, perhaps, there would still be planets, old worlds orbiting old stars, places where life might have emerged billions of years ago and then ended when the darkness came. Ghost worlds in ghost clusters, drifting through the void, carrying the fossilized remains of civilizations that rose and fell long before humanity even existed. All of it is invisible, all of it silent, all of it alone in the darkness, waiting for a time that might never come when light would return and reveal the secrets they held. Even without light, the Milky Way would remain a vast gravitational kingdom of planets, black holes, dust, gas, and invisible motion. A silent galaxy drifting through eternity. And so we come to the end of our journey through darkness, back to where we began, but seeing it differently now, understanding more deeply what it would mean. The Milky Way would still exist. That's the essential truth. The absence of light wouldn't unmake the galaxy, wouldn't dissolve the structure that gravity had built over billions of years. Every star would still be there, still massive, still holding its planets in orbit. Every black hole would still curve spacetime around it. Every cloud of gas and dust would still drift through the interstellar medium. The galaxy would be a kingdom as it always has been, a realm ruled by gravity, by the fundamental force that pulls matter together and keeps it organized. That kingdom would persist. It would continue operating according to the same laws of physics that have governed it since its formation. Planets would still orbit their dark suns. Moons would still circle their planets. Asteroids would still collide and fragment. Comets would still follow their long elliptical paths through the solar systems. All of the motion, all of the mechanical clockwork of the cosmos would continue, uninterrupted, unaffected by the absence of light. The galaxy would still rotate. Once every couple of 100 million years, the spiral arms would complete another circuit around the center. The stars would maintain their places in those arms, or drift slowly from one arm to another over millions of years. The overall structure, the grand design of the Milky Way, would persist even though it could no longer be seen. It would be a silent symphony, a dance performed in darkness, motion without visibility, structure without observation. The universe continues to exist, continuing to evolve, continuing to follow the patterns written into the laws of nature, regardless of whether anyone could witness it. And perhaps there's something profound in that, something humbling, the realization that the universe doesn't exist for our benefit, that it doesn't need us to observe it in order to be real, that it would carry on, indifferent to our presence or absence, governed by forces older and more fundamental than consciousness itself. The Milky Way would drift through space. It would move among the other galaxies in the local group, still bound to them by gravity, still on course for its eventual merger with Andromeda. It would age, slowly, imperceptibly, but inevitably, and it would remain, long after any memory of its bright past had faded, long after the last civilization had risen and fallen, long after everything that had once observed the stars had returned to dust. A silent galaxy, a dark galaxy, but still a galaxy, still real, still present in the universe, still home to everything we ever were, everything we ever knew, everything that ever mattered to us. Drifting through eternity, patient, enduring, waiting in the darkness for an end that might never come, or for a new beginning that might someday ignite the stars again and fill the cosmos with light. But until that moment, if it ever comes, the Milky Way would remain what it had become. A ghost in the universe, a memory made solid, a kingdom of darkness, vast and silent, holding within it all the mass and motion and structure that once created the most beautiful sight in the heavens. And in that darkness, in that silence, in that invisible persistence of reality, there would be a kind of terrible, lonely beauty, the beauty of things that endure beyond sight, beyond witness, beyond hope, the beauty of existence itself, continuing simply because that is what existence does. Forever,